Hello there, and welcome to Life Beyond Seen, where curiosity settles down for the night and the stranger corners of science are given a quieter voice. Tonight, we are heading far below the bright surface of the sea, down past the fishing boats and the coral shelves and the places most swimmers are happy to imagine are empty. We're going into water so deep that sunlight never reaches it, into a world where pressure can crush steel, where meals are rare, and where survival has produced some truly unsettling arrangements. Our subject tonight is the deadliest deep-sea parasite still lurking in the ocean. Now, that word parasite has a way of making the shoulders rise just a little, doesn't it? It is not quite as charming as dolphin, not quite as marketable as whale, and it rarely appears on postcards unless the postcard is trying very hard to ruin someone's beach holiday. But parasites are among the most successful life forms on Earth. They are patient, they are efficient, they do not need applause, they do not need a heroic reputation, they only need a host, a weakness, and enough time. And the deep ocean, with its darkness, its scarcity, and its constant pressure to adapt or die, has given them plenty to work with. If you pause for a moment and picture the deep sea, you might imagine giant squid, glowing fish, maybe a shark sliding past like an expensive nightmare in slow motion. Most of us, when we think of danger in the ocean, think of jaws and speed and obvious things. We picture something large enough to see coming, something with teeth that have their own publicist. But some of the most successful killers below the waves are not the hunters that chase. They are the ones that attach, infiltrate, drain, burrow, hijack, and wait. They make a living not by outrunning their prey, but by becoming part of it, which from a biological perspective is clever, from the host's perspective less ideal, and perhaps that is what makes parasites so unnerving. A predator may tear, bite, swallow, and move on. It is violent, yes, but at least it is direct. A parasite is slower. It gets closer. It feeds while the host is still alive. In some cases, it changes the host's behaviour. In others, it slowly replaces body tissue, steals nutrients, consumes blood, or turns a living creature into something that is still moving, but no longer quite in charge of itself. It is one thing to be chased in the dark. It is another thing entirely to discover that the danger is already inside you, already attached to you, or has made your own body part of its plan. That really is the sort of world we are entering tonight. Not a world of movie monsters in the usual sense, but a world of very real organisms that have evolved in ways that are colder, stranger, and often more effective than anything a screenwriter would dare invent without being accused of overdoing it. Before we go any deeper, I would love to know where in the world you are listening from tonight, and what sort of hour it is in your corner of things. Is it late evening, with the room finally quiet? Is it well past midnight, when the house settles and every small sound seems more important than it was during the day? Or maybe it is early morning, and you have made the truly bold choice to begin your day with parasitic horror from the deep ocean, which I have to respect. There is something fitting, I think, about hearing a story like this while the rest of the world is slowing down. The deep sea is a place without sunlight, without morning or evening in the way we know them. It simply remains dark, and life goes on in that darkness with remarkable determination. And if you find this kind of journey soothing in its own strange way, if you enjoy learning about the natural world when it is presented a little more gently, I would be very grateful if you gave the video a like and maybe subscribed as well. It helps this calm little corner reach other people who might enjoy drifting off to stories about things they would absolutely not want touching their face in real life. Science can be many things. Tonight it happens to be damp, patient, and deeply unsettling. So settle in. Let your breathing slow a little. Let the day loosen its grip. We are going down now, past the places mapped for tourists and into the older, quieter part of the sea, where life has had millions of years to solve a brutal problem. How do you survive when food is scarce, when movement costs energy, and when every opportunity may be the only one you get for weeks or months at a time? One answer, as it turns out, is this. You stop looking for an occasional meal, and instead you find a body that can carry your meal around for you. That idea alone explains a great deal about why parasites thrive so well in the ocean, and especially in the deeper parts of it. A parasitic way of life can be ruthless, but it is also economical. If you can attach yourself to a host, enter its tissues, live in its gut, cling to its gills, or lodge yourself beneath its skin, you solve several problems at once. You gain transport, you gain food, you gain shelter. Sometimes you even gain a convenient way to reproduce. From an evolutionary standpoint, it is hard not to admire the efficiency, even while every other part of the human mind is recoiling and saying no, absolutely not, thank you very much. The deep ocean makes this strategy even more useful. Down there, resources are patchy. A creature may travel long distances and find very little. Carcasses sink only occasionally. Prey is not always easy to catch. Light is absent. Temperatures are low. Pressure is immense. Everything about that environment favours solutions that conserve energy and waste very little. A parasite, especially a good one, is built around that principle. It does not spend more than it must. It does not hunt if it can cling. It does not chew if it can absorb. It does not build a luxurious existence. It takes just enough from the host to continue, and then it keeps going. Of course, just enough can still mean a great deal if you happen to be the one being used. There is also a common mistake people make when they imagine parasites. We tend to picture them as tiny, almost incidental, like unpleasant footnotes attached to otherwise interesting animals. But in the ocean, that is not always the case. Some are large enough to be immediately visible. Some dramatically alter the bodies of the creatures they inhabit. Some fill mouths, replace organs, swell in the gut, or hang from the skin. Some begin life in one host, mature in another, and reproduce in a third, moving through the food web with a level of logistical planning that would be impressive if it were not so revolting. In the deep sea in particular, many parasites are not just background nuisances. They are major ecological players. They shape behaviour. They influence who eats whom. They can weaken populations, change reproductive success, and redirect energy through the ecosystem in ways most people never think about when they look out at the water and see only a smooth blue surface. And that surface really hides the problem beautifully. The ocean is very good at concealment. A forest can show you claw marks on bark. A desert leaves tracks. Even a storm gives notice. But the sea covers its workings under motion and reflection. It looks open. It looks clean from a distance. Yet beneath that moving skin is an enormous layered world of feeding, drifting, hiding, and being consumed. Parasites fit that hidden logic perfectly. They are creatures of access. They rely on not being noticed until the work is already underway. Some of the most remarkable deep-sea parasites do not simply feed on a host. They change it. That is where the story becomes especially difficult to forget. When a parasite alters behaviour, it stops seeming like a simple freeloader and starts looking more like a biological saboteur. There are parasites that can make a host more reckless, slower, weaker, or easier for the next predator in the chain to catch. There are parasites that redirect growth, drain reproductive energy, and effectively convert a living animal from a self-directed creature into a kind of delivery system. A body with a mission it did not choose. In shallow waters, scientists have documented many examples of this sort of manipulation. In deeper waters, the relationships are harder to observe, but evidence keeps mounting that similar strategies are at work there too, shaped by the peculiar demands of darkness and scarcity. And then there is the simple matter of anatomy. Deep-sea parasites are not designed for charm. This will not surprise you, I know, but it is worth stating clearly. When nature is under pressure, appearance becomes a secondary concern. Hooks, spines, rasping mouth parts, sucker discs, anchoring claws, burrowing heads, thread-like bodies, expandable egg sacs, tissue-dissolving chemicals. These are not glamorous features, but they are useful ones. In the depths, Utility wins. You do not need elegance when your job is to hold onto a fish in crushing darkness and feed for as long as possible before something larger eats both of you. One of the reasons this subject has fascinated marine biologists for so long is that deep-sea parasitism forces us to rethink what survival looks like. On land, we admire speed, strength, and strategy that feels active. We like the drama of the chase. In the deep ocean, survival is often less theatrical and more patient. It is not always about attacking. Sometimes it is about enduring. Sometimes it is about waiting in the right place until another animal swallows you by mistake, or brushing past at exactly the wrong moment. Sometimes it is about beginning life as a free-swimming larva no one would notice, and ending it anchored inside the muscle, blood supply, or body cavity of something far larger than yourself. There is something bleakly practical about it. The deep ocean has very little interest in fairness. It rewards whatever works, and what works down there can be remarkably grim. It also helps to remember that parasites are not some bizarre side note in evolution. They are everywhere. Many scientists estimate that parasitic lifestyles have evolved over and over again across different branches of life because, inconveniently for our peace of mind, it is often a very effective strategy. There are parasitic worms, crustaceans, copepods, isopods, protozoans and more, each with its own method, each exploiting a different weakness. The ocean is especially rich in these relationships because it is so interconnected. Water carries larvae. Predators swallow prey whole. Filter feeders process huge volumes. Scavengers gather at carcasses. One body becomes another body's meal, and parasites take full advantage of those transitions. A host eaten by a larger animal is not always the end of the parasite's story. Sometimes it is the whole point. If that sounds uncomfortably organised, that is because it is. Parasites are often specialists. They may rely on a particular species, a particular organ, a particular life stage, or a very specific chain of events. One missed step and the cycle fails. Yet those cycles have persisted because the ocean keeps delivering the necessary opportunities. A small fish eats an infected crustacean. A larger fish eats the small fish. A shark eats the larger fish. Somewhere along that ladder the parasite grows, changes form, mates, reproduces, and begins again. The host thinks it is having a bad day. The parasite, meanwhile, is simply progressing through its schedule. There is something almost administrative about that, which I find unnerving in its own special way. Not chaos, not madness, just process. For us, the deep sea often represents mystery, because we cannot easily go there. It is expensive to study, difficult to access, and often physically hostile to our equipment. Entire regions remain poorly understood. New species are still being discovered. Behaviours are still being documented. Relationships that may be common down there can remain invisible to us simply because we have not watched long enough, or because the animal comes up damaged, or because the parasite detaches before collection, or because something that looks like a deformity turns out to be an organism in its own right. The more we look, the stranger it becomes. Not because the deep sea is trying to shock us, but because it has been solving life's problems without consulting our comfort. And so, when we talk about the deadliest deep-sea parasites still lurking in the ocean, we are not talking about monsters in a dramatic sense. We are talking about real biological systems that continue right now whether anyone is watching or not. Somewhere in the dark, a parasite is attached to the gills of a fish, feeding with calm determination. Somewhere else, a larval stage is drifting until it finds the correct host. Somewhere a body is being hollowed slowly, blood is being taken in small regular meals, tissues are being replaced, and behaviour is being altered in ways the animal itself cannot understand. That is not fantasy. That is dinner in the abyss. It is also, in a strange way, a reminder that nature is not arranged around our preferences. We often like to divide living things into neat categories: beautiful animals, useful animals, dangerous animals, cute animals, and the unfortunate group that makes us regret having eyes. Parasites do not fit comfortably into any of these. They are not villains, they are not mistakes, they are solutions. Brutal ones, yes, but solutions all the same. They tell us something important about what life will do when pushed into difficult conditions. It will improvise, it will economize, it will turn another body into shelter if it must. It will survive in ways that seem almost rude. And if you are now feeling just a little more aware of your own skin, your own mouth, your own general preference for being left uninhabited, that is understandable. I suspect it is one of the few topics in biology that can make a person appreciate their organs with renewed sincerity. Very few of us go through the day thinking, how wonderful that my tongue remains fully my own. Yet after tonight, you may find yourself unusually grateful for that arrangement. What makes the coming journey especially interesting is that not all these parasites kill quickly. In fact, many of the most effective ones do the opposite. A dead host can be useful certainly, but a living host can carry you farther, feed you longer, and place you exactly where you need to be next. So deadliest does not always mean immediate. Sometimes it means relentless. Sometimes it means so well adapted that the host has almost no chance once the process begins. Sometimes it means the parasite reaches into the basic functions of feeding, breathing, moving, or reproducing, and slowly redirects them for its own use. Death may come later, the takeover starts much earlier, and that is where we're headed now. Not in a rush, and not all at once, but carefully, one creature at a time, into a catalogue of bodies used as homes, mouths turned into shelters, muscles turned into food stores, and instincts bent in directions that serve something small, silent, and entirely committed to getting what it needs. Because before we can understand the worst of what lurks down there, it helps to begin with the simplest truth of all. In the deep ocean, hunger rarely goes to waste, and some of the most successful feeders are the ones that learn not to chase their prey at all but to live with it. If the deep sea has a ruling law, it is not beauty, and it is not fairness. It is hunger. Constant, practical, unsentimental hunger. The kind that shapes bodies, behaviours, and entire ways of life. The kind that does not care whether a solution seems elegant or horrifying, only whether it works. And in the ocean's deepest reaches, where food can be painfully scarce and every calorie matters, that hunger has helped produce some of the most efficient parasites on Earth. Up near the surface, life can feel almost generous by comparison. Sunlight reaches the water, tiny phytoplankton bloom, small animals feed on them. Bigger animals feed on the smaller ones. Energy moves through the system with some regularity. Not evenly, of course. Nature has never been especially committed to equal distribution, but there is at least a steady input. The sun shows up. Plants and plankton do their part. Something is always growing, drifting, being eaten, or trying very hard not to be. The deep sea does not get that luxury. Once you move far enough down, sunlight disappears completely. There is no photosynthesis in the usual sense, no waving forests of seaweed, no broad green base of easy food production. Down there, most of life depends on what falls from above, what drifts in from elsewhere, or what can be taken directly from another living body. It is an economy built on leftovers, accidents, rare windfalls, and relentless efficiency. If the upper ocean is a busy market, the deep sea is a cold, dim back alley, where every scrap is noticed and nothing goes unused for long. Marine biologists sometimes talk about marine snow, which sounds charming until you remember what it really is. It is not snow in the pleasant winter postcard sense. It is a slow, continuous shower of dead plankton, fecal pellets, mucus, bits of decaying tissue, tiny shells, discarded matter, and all the other fragments of surface life drifting downward through the water column. It feeds countless deep-sea organisms, and without it, many of them would not survive. But marine snow is not exactly a banquet. It is sparse, uneven, and often nutritionally poor by the time it reaches great depth. Imagine trying to live on whatever crumbs happen to float off the tables of an entire city, except the crumbs are soggy, half decayed, and may take days or weeks to arrive. That is not an environment that encourages wastefulness. Then there are the bigger gifts from above: a dead fish, a jelly, a turtle. If fortune really smiles, a whale fall, which is the name given when a whale carcass sinks to the seafloor and becomes for a while an entire ecosystem. These events are extraordinary. They can feed large communities for years. Scavengers gather, worms burrow, crustaceans swarm, bacteria bloom. The deep sea, which often looks sparse and empty, suddenly becomes crowded with mouths. But that's the point. These events are rare enough that when they happen, everything nearby must be ready to exploit them fast. It is not unlike putting one sandwich in the middle of a football stadium and announcing that lunch has been served. Politeness would not survive the first few seconds. Scarcity changes what counts as a good feeding strategy. In a place where prey is limited and energy is expensive, chasing down meals is risky. Fast movement cost fuel. Searching cost fuel. Growing large muscles cost fuel. Missing a hunting opportunity after spending all that energy can be disastrous. So the deep sea rewards any method that reduces those costs. Ambush works. Scavenging works. Filter feeding can work in the right place. And parasitism, perhaps more than almost any other strategy, works beautifully in a world where free food is rare, but living bodies are everywhere. A host is not just a meal. That is the important thing. A host is a meal that moves, breathes, circulates nutrients, and may continue doing so for a long time. A host can also provide warmth relative to the environment, chemical stability, physical shelter, and in some cases transport into entirely new parts of the ocean. If you are a parasite in the deep sea, finding the right host can solve several life problems at once. You're no longer waiting for scraps to drift your way. You're connected directly to a supply line. It may not be a very happy supply line from the host point of view, but it is a supply line nonetheless. This is one reason parasites can be so successful where food is unpredictable. They reduce uncertainty. Not completely, of course. A parasite still has to find a host, survive the host defences, and often move through a very complicated life cycle. But once established, it gains a reliability that many free-living animals never have. A fish might go days without a proper meal. A parasite attached to that fish has a front-row seat to whatever nutrients continue to move through the body. That is a tremendous advantage in a place where opportunities can be few and far between. There is also the matter of scale. We are used to thinking of predators as obvious threats because they are dramatic. Teeth, speed, sudden violence. Parasites do not usually announce themselves with that kind of flair. They work in smaller, steadier withdrawals. A little blood here, a little tissue there, some nutrients diverted, some reproductive energy stolen. Sometimes they weaken the host only gradually. Sometimes they leave it alive for long periods, because that is exactly what makes the arrangement profitable. A tiger that gently takes one bite of a deer every few days would be considered a terrible tiger. A parasite that does this on a biological level is considered highly competent. This hidden hunger becomes even more interesting when you remember that many deep-sea animals are already living close to the edge of what their environment allows. They do not have endless reserves to spare. Many grow slowly, many reproduce infrequently, some may go long stretches with very little food. In that kind of life, even modest parasitic drain can matter a great deal. A host that loses blood, nutrients, muscle function, or digestive efficiency may not die at once, but it becomes weaker, slower, and less resilient. That can mean poorer growth, fewer offspring, less ability to flee predators, and less chance of surviving the next stressful period. The parasite does not always need to kill directly. Sometimes all it has to do is tip the host slightly closer to failure and let the deep sea finish the rest. The ocean also makes it easier for parasites to spread in ways land environments often do not. Water is an excellent medium for drifting eggs, larvae, spores, and microscopic stages that need to find new hosts. It connects habitats. It carries scent, waste, chemical cues, and bodies. It allows one infected animal to become part of a much larger chain. A parasite released into the water does not need roads, luck, or a train ticket. It needs currents, proximity, and timing. That may sound simple, but evolution has had an extraordinary amount of time to refine those details. Some parasites use the food web itself as a transport network. A tiny crustacean becomes infected. A fish eats the crustacean. A squid eats the fish. A shark eats the squid. At each step, the parasite changes stage, grows, or moves closer to its final destination. That kind of life cycle only works in a system where bodies are regularly swallowed whole, and one animal's meal becomes another animal's habitat. The ocean is very good at providing those opportunities. It is, if you like, a conveyor belt of flesh, with parasites quietly hitching rides between stations. And because deep-sea feeding can be so opportunistic, many animals are not especially picky when a chance at food appears. A scavenger may rush a carcass and ingest whatever is attached to it. A predator may snap up prey in darkness with limited opportunity to inspect it carefully, which is an understandable oversight in the circumstances. Filter feeders process enormous volumes of water and whatever comes with it. Parasites exploit all of this. They do not need every encounter to work. They only need enough of them to succeed over time. In a vast ocean with endless repetitions of feeding and being fed upon, even low probability chances can become reliable strategies. There is another side to hunger in the deep sea that matters just as much. Hosts themselves are often hungry. That may sound obvious, but it has consequences. A hungry animal is more likely to take risks, consume unfamiliar prey, scavenge questionable material, or ignore subtle warning signs. This makes it easier for parasites to enter the body in the first place. Some parasites rely on exactly this. Their eggs or larval forms do not force their way dramatically into a host. They wait to be eaten. A fish or crustacean, driven by hunger, in an environment where food is never guaranteed, does the rest. It swallows first and regrets later, which, to be fair, describes a surprising number of biological interactions. The deep sea also encourages close relationships around any source of food. When a carcass arrives, animals gather. When a host is weakened, scavengers and opportunists may converge. When one species uses another as shelter or transport, others may attach in turn. This creates a situation in which individual bodies become small communities. A fish may carry its own bacteria, internal worms, gill parasites, skin-feeding copepods, and scavenging hitchhikers all at once. It is less a single customer in the ecosystem, and more a crowded apartment building with poor tenant screening. That may sound exaggerated, but marine scientists have repeatedly found that one host can support multiple parasitic species at the same time, each exploiting a different tissue or body region. One may target the gut, another the blood supply, another the gills, another the mouth, another the muscle. The host continues swimming through darkness like a badly managed vessel carrying a collection of freeloaders, boarders, and tiny specialists all taking their share. It is not hard to see why this matters. In a place where every calorie counts, losing even small amounts to multiple parasites can become a serious burden. And yet hunger does not only shape the parasite, it shapes the host's defences as well. Defending yourself from parasites takes energy. Immune responses are costly. Tissue repair is costly. Behavioural avoidance is costly. Grooming, cleaning, producing mucus, replacing damaged blood cells, maintaining strong barriers in skin and gut lining, all of this has a metabolic price. In the deep sea, organisms do not always have abundant spare energy for those defences, So parasites are not simply taking advantage of a wealthy, well-protected body. Often they are invading hosts that are already making difficult choices about where their limited resources should go. Grow or defend, reproduce or repair, swim or fight infection. The answer is not always favourable to the host. This is part of what makes the deep sea such a useful place for parasitic strategies to flourish. Hunger is not just the lack of food, it is the pressure created by that lack. It influences behaviour, anatomy, immunity, reproduction, timing, movement, and risk. It narrows margins. It turns compromise into daily life. Under those conditions, a parasite does not need to be spectacular. It needs to be economical and persistent. The environment will do the rest. There is also a psychological reason these creatures disturb us so much. We like to imagine the dangerous parts of nature as external. The shark is out there, the storm is out there, the cliff edge is over there, and with even modest effort we can avoid stepping off it. Parasites are different because they turn danger inward. They blur the line between the creature and the thing harming it. When hunger drives a parasite to live inside a host, the host becomes part of the feeding event. Not prey in the usual single, completed sense, but infrastructure. A place where the meal continues over time. Something about that arrangement feels less clean to us, even if in ecological terms it is just another survival strategy. In the deep ocean, where visibility is limited and direct observation is difficult, this hidden hunger can go unnoticed for a long time. A fish brought up from depth may show swelling, lesions, strange protrusions or missing tissue, and only on closer inspection does it become clear that what looked like damage is in fact occupation. A bulge in the body cavity may be a worm, a distorted mouth may contain a crustacean, a wasted, thin animal may be carrying internal feeders that have quietly redirected its resources for months. Researchers studying deep-sea specimens sometimes find entire stories of feeding and being fed upon written into the anatomy, like records no one intended to keep. The deeper we look, the more it becomes clear that hunger in the ocean is not always solved by hunting harder. Often it is solved by embedding yourself in the process. Deep-sea parasites are not just responding to hunger, they are products of a food system where access matters more than force, and where certainty matters more than speed. They have evolved not because the deep sea is grotesque, though it can certainly give that impression at 2 a.m, but because it is demanding. It rewards anything that makes feeding more reliable, and that brings us to a particularly unsettling detail. Once a parasite has solved the problem of feeding, there is still another problem to solve. How do you ensure that your host remains useful long enough? How do you stop it from shaking you off, avoiding danger, or behaving in ways that interrupt your life cycle? In some cases, the answer is simple attachment and endurance. In others, the answer becomes far more intrusive. The parasite begins to influence the host's decisions, movements, or instincts. Hunger, having gained entry, starts to take the controls. That is where things become especially difficult to ignore, because a parasite that only feeds is unpleasant enough. A parasite that turns a host into something easier to use is operating on another level entirely, and the deep ocean, with its scarcity and ruthless efficiency, has given that strategy plenty of room to succeed. There is something especially unsettling about a parasite that does not merely feed on a host, but starts influencing what that host does. A blood feeder is bad enough. A tissue eater is unpleasant enough. But a parasite that interferes with behaviour crosses a line that most creatures, including us, find deeply uncomfortable. It is one thing to lose strength, it is another thing to lose direction. And in the ocean, including the deep and dim layers where life is already forced into hard bargains, some parasites have evolved in precisely that direction. They do not just take from the body, they alter the choices the body makes. Now, to be clear, not every host-manipulating parasite is literally steering its victim like a tiny driver gripping a biological steering wheel, though the image is unfortunately memorable. What usually happens is more subtle, and in some ways even more effective. The The parasite changes chemistry, damages key tissues, drains energy, affects hormones, interferes with sensory systems, or alters the host's normal balance between caution and risk. The result is not mind control in the cinematic sense. It is something quieter. The host becomes easier to catch, easier to exploit, more likely to move into dangerous areas, less likely to avoid predators, or more likely to behave in ways that help the parasite move to its next life stage. That last part matters a great deal because many marine parasites do not spend their whole lives in one host. They move through several. A small crustacean may carry the early stage, a fish may carry the next. A larger predator may become the final destination, the place where the parasite matures and reproduces. In that sort of system, getting from one host to another is everything, and if influencing the middle host makes that transfer more likely, then evolution is going to favour any parasite that can manage it. The basic logic is brutally simple. Suppose you are a parasite living inside a small fish, but you need that fish to be eaten by a larger predator in order to continue developing. The fish, being inconveniently attached to its own survival, may spend a great deal of time avoiding exactly that outcome. It hides, it schools, it darts away from shadows. It behaves, in other words, like a creature that would prefer not to become lunch. From the parasite's point of view, this is an administrative problem. The solution is not always to kill the host. A dead host drifting into the dark may never be eaten by the correct animal. No, much better to keep it alive, but a little slower, a little bolder, a little worse at fear, and so the host begins to change. Marine scientists have documented many parasite-related behavioural shifts in ocean animals, especially in shallower waters where direct study is easier. Infected fish may swim closer to the surface, linger out in the open, react less strongly to predators, or move in ways that make them more conspicuous. Small crustaceans may become unusually active, more exposed, or more likely to enter places where they are readily consumed by the next host species. Worms, protozoans, and parasitic crustaceans can all participate in these altered states, each in its own way, each using the host not only as food but as transportation. In the deep ocean, observing this directly is more difficult, because the environment is so hard to access, and the animals are not always thrilled to participate in long-term behavioural studies. But the patterns seen across marine ecosystems strongly suggest that similar manipulation is at work in deeper layers as well. The ocean does not become more forgiving with depth. If anything, the pressure to make each life stage transfer count becomes greater. Food is sparse, encounters may be rare. A parasite that can improve its odds by nudging host behaviour even slightly gains a serious advantage. One of the classic examples of parasite-driven manipulation in marine systems involves trematodes, a group of parasitic flatworms with life cycles that can be so complicated they seem less like biology and more like a conspiracy conducted through seafood. These parasites often begin life in one host, such as a snail, and later move into fish or other animals before reaching a final predator host, often a bird or larger fish. Along the way, they may alter the behaviour of the intermediate host in ways that make it more visible and more vulnerable. A fish that should stay low in the water may rise higher. A normally cautious host may become careless. A creature that ought to avoid light may drift into it. The parasite does not need complete control. It only needs enough of a change to increase the chance of being eaten by the right next animal. There is a cold efficiency to this. The host instincts were shaped by evolution to keep it alive long enough to reproduce. The parasite's interests are entirely different. If the parasite benefits from the host being eaten, then the host's survival systems become obstacles to be worked around. Not by reason, of course, not by persuasion. The parasite is not sitting inside the fish explaining the benefits of poor decision-making. It is influencing biochemical systems, altering tissues, diverting nutrients, stressing organs, or producing molecules that affect the nervous system. The outcome may look like recklessness, but the machinery underneath it is physical. and because it is physical, it can be remarkably difficult for the host to resist. There are marine parasites that infect the eyes, for example, which is a particularly rude approach. Some larval trematodes lodge in ocular tissues, including the lens or nearby structures, impairing vision. Now imagine you're a fish in dim water where seeing well is already a challenge. Your life depends on noticing predators in time to react. Your ability to hunt or avoid being hunted is tied to limited sensory information, and then a parasite arrives and clouds that information further. The fish may not become a puppet in the dramatic sense, but it becomes easier prey, and that may be exactly what the parasite needs. If the parasite's final host is a larger predator, then blinding or partially disabling the intermediate host is a very effective shortcut. Other parasites alter body condition in ways that change behavior indirectly. An infected host may become weaker, slower, less coordinated, or more desperate in feeding. A hungry fish takes more risks. A weakened crustacean spends less time fleeing. A host drained of nutrients may not maintain normal schooling behavior or predator avoidance. This is not always a direct nervous system hack. Sometimes it is simple sabotage. Break enough systems and the behavior changes on its own. In crustaceans, the story can become stranger still. Some parasitic barnacles and isopods are not content merely to feed. They reorganize the host's priorities. There are species that infect crabs and effectively castrate them, redirecting the host's resources away from reproduction and toward maintaining the parasite. In some cases, infected crabs begin to behave as though the parasite's external reproductive structure were their own brood mass, grooming and protecting it. That is one of those facts that sounds made up by someone trying too hard, but it is well documented. The parasite has not simply stolen nutrients. It has inserted itself into the host's reproductive and behavioural system so successfully that the crab begins caring for the parasite's offspring. That is where the word puppet starts to feel less like exaggeration and more like a practical description. Now, those famous parasitic barnacles are often discussed in shallower marine environments, but the principles behind this kind of manipulation matter for the deeper sea as well. In dark habitats where reproductive opportunities may already be limited and contact between individuals is less frequent, any parasite that can redirect host energy, suppress competing biological functions, or induce care-like behavior gains a substantial edge. Deep-sea crustaceans, fish, and other animals are not exempt from these pressures. If anything, the scarcity of opportunity in the deep makes it even more useful for parasites to keep hosts alive, active, and behaviourally useful for as long as possible. There is also the issue of vertical movement in the water column. Some deep-sea animals migrate upward at night to feed and descend again by day, a daily commute known as diel vertical migration. It is one of the largest synchronized animal movements on Earth, though fortunately much of it occurs where we do not have to watch. For parasites, this movement presents opportunity. A host travelling between layers can expose the parasite to new predators, new environments, and new transfer chances. If infection changes how well the host performs this migration, or how exposed it becomes during it, then the parasite may gain exactly the sort of host-to-host transition it needs. A fish that rises too high, lingers too long, or fails to descend efficiently becomes a better target. A squid weakened at the wrong moment may drift within reach of a predator it would normally evade. A small crustacean, whose escape response is dulled, becomes an easy meal. In the deep sea, where direct observation is limited, such outcomes may look like simple bad luck. But when infection patterns line up with predictable shifts in behaviour or body condition, the deep explanation begins to emerge. What looks like poor judgment may actually be the parasite's best work. And it is worth noting that host manipulation does not always benefit the parasite by making the host easier prey. Sometimes the goal is to keep the host in place. A parasite may benefit from reducing movement, increasing lethargy, or impairing feeding efficiency in a way that keeps the host weakened but available. In other cases, manipulation may influence social behaviour, mating behaviour, or habitat use. The host may avoid normal shelter, fail to school properly, or spend more time in conditions that increase transmission. There are many routes to success, and evolution does not care whether the method seems elegant. It cares whether more parasites make it to the next generation. For deep-sea parasites, one of the most valuable outcomes is often predictability. The ocean is vast, encounters are uncertain. If you can make a host do something that narrows that uncertainty, even a little, you're improving your odds. A host that carries you into a predator's range is useful. A host that protects your brood is useful. A host that continues circulating nutrients while no longer reproducing is useful. A host that becomes bold enough to get eaten, but not so impaired that it dies too soon, is ideal. This is not mindless feeding. It is strategy written into anatomy and chemistry. Even some of the most famous fish parasites hint at this blurred line between feeding and influence. Consider parasitic copepods and isopods that attach to the mouth, gills, or skin. Their immediate effect may be physical damage, blood loss, or interference with normal function. But those physical effects can cascade into behaviour. A fish with a damaged mouth may feed differently. A fish whose gills are compromised may tire more quickly and avoid normal activity. A fish carrying an invasive crustacean in its mouth, replacing or obstructing tissue, is not just being fed upon, it is living under altered rules. Its choices narrow, its reactions change, it may swim, hunt, and respond to threats in ways that are no longer fully its own. There is a particularly grim sort of marine manipulation in parasites that feminize, castrate, or hormonally disrupt hosts. Some crustacean parasites can alter sexual characteristics and reproductive development in infected animals, effectively turning the host biology away from its own continuation and toward the parasite's maintenance. Again, the goal is not drama, it is resource redirection. Reproduction is expensive. Gonads are expensive. Mating behavior is expensive. If a parasite can shut those processes down, it frees energy for itself. If it can also shift host behavior toward brood care or reduce competition, so much the better. The deep ocean is full of species with already delicate reproductive timing. Encounters between mates can be rare. Energy investment in offspring can be substantial. A parasite that interrupts those systems may not need to kill a host to have a deadly ecological effect. It can erase that host's future contribution to the population, while keeping the body alive as a working platform. For the individual, the result is a kind of biological theft. For the population, enough of these cases can become a serious pressure over time, and then there is the matter of timing. A good manipulative parasite does not necessarily interfere immediately. In many cases, early infection is quiet. The host continues its life while the parasite grows, develops, or waits for the correct stage. Only later, when transfer or reproduction becomes possible, do the more obvious changes appear. This makes evolutionary sense. There's no benefit in ruining the host too soon. The parasite is not interested in tantrums. It is interested in scheduling. That scheduling can make the whole process feel even colder. The parasite waits until the host is in the right size class, the right season, the right location, or the right internal state. Then the changes become more apparent. A host moves differently, feeds differently, risks more, protects something it should not. By the time anyone looking from outside notices, the useful part of the manipulation may already be nearly complete. One reason scientists care so much about these systems is that they reveal how behavior itself can become part of an ecosystem's invisible machinery. We tend to think of behavior as belonging entirely to the animal performing it. The fish flees because it wants to live. The crab grooms because it is caring for its young. The crustacean rises because it is feeding. But parasites complicate that picture. They turn behavior into contested territory. The host body may still be moving under its own power, but the reasons behind those movements can be influenced by something else entirely. That is a difficult idea to get comfortable with, which may be why it stays with people. In the deep sea, where so much already feels alien, this becomes one more reminder that survival is not always a clean contest between hunter and hunted. Sometimes the real struggle is inside the host, hidden behind ordinary movement. A fish may appear simply unlucky, when in fact it has been chemically nudged toward danger for weeks. A crustacean may seem devoted to brood care, while actually tending the reproductive ambitions of a parasite. A weakened animal drifting too high in the water column may not be making a mistake at all. It may be completing someone else's life cycle. And the unsettling thing is that, from the parasite's point of view, this is not cruelty. It is efficiency. There is no malice in it. No theatrical villainy. Only selection, generation after generation favouring those tiny interventions that improve transmission, improve feeding, improve timing. The result looks calculating because evolution often produces outcomes that feel that way, even though no single creature planned them. The parasite did not sit down and invent manipulation. It inherited it, refined it, benefited from it, and the host inherited a body vulnerable to exactly those sorts of pressures. That is the kind of hidden negotiation taking place all through the ocean, especially in places where scarcity leaves little room for wasted chances. Hunger creates the need. Manipulation improves the odds. And once a parasite has found a way not only to live in a host, but to turn the host into a more useful vehicle, the relationship changes from feeding to control in all but name. Of course, to keep that control, or even to begin it, a parasite first has to solve another problem. It has to stay attached. It has to hold on through pressure, movement, current, struggling flesh, and the simple fact that living animals are generally not enthusiastic about being occupied, which is why so many of the deep sea's most successful parasites come equipped not just with clever life cycles, but with the physical tools to anchor themselves securely, feed steadily, and make sure they are not easily removed once the work begins. Which is why so many of the deep sea's most successful parasites come equipped with something that looks less like refinement and more like determination made physical. If you cannot chase down meals with speed, and if your entire life depends on remaining fixed to a host that is swimming, thrashing, feeding, diving, or scraping past rough surfaces in cold black water, then you need hardware. Not elegance, not grace. Hardware, teeth to bite, hooks to anchor, mouthparts to clamp, spines to brace, suckers to seal, barbs to make leaving difficult for everyone except the parasite itself. This is one of the least comforting truths about life in the abyss. Parasites there are not just passive drifters that happen to end up on the wrong fish. Many are built for attachment with startling commitment. Their bodies often look as if every design choice was made by asking one question only. How do I stay here once I've found something alive? That question matters because attachment in the ocean is not trivial. Even in shallower water, a host is not a calm platform. It moves, it flexes, it produces mucus. It may rub against rock, sediment, coral, or other animals. Water rushes over skin and through gills. Jaws open and close. Blood pulses. Fins beat. A parasite that feeds externally or partly embedded in tissue has to cope with all of this while remaining secure enough to feed and often secure enough to reproduce. Down in deeper water, the problem becomes even more serious because energy is precious. If you lose your hold and drift away, there may not be another host along any time soon. Missing one chance can mean the end of the line, so deep-sea parasites tend to be practical in the way a bolt cutter is practical. Their structures are there to solve a problem, and the solution is rarely subtle. Take parasitic copepods for a start. Now, copepods in general are tiny crustaceans and are among the most numerous animals on Earth, which is already faintly alarming once you begin paying attention to them. Many are harmless drifters, an important part of marine food webs, but some lineages took a darker turn and became highly specialized parasites. These are not the neat, streamlined little planktonic forms you might see under a microscope in an introductory marine biology class. Parasitic copepods often look transformed almost beyond recognition. Their bodies can become elongated, twisted, sack-like, or bizarrely asymmetrical. Their legs may be reduced. Their free-living grace disappears. In its place comes an architecture built around entering tissue, gripping host surfaces, and feeding with patience. Some of these copepods anchor themselves with modified head structures that penetrate deeply into flesh. They may begin with a larval stage that swims freely, searching for a host, and then, once contact is made, the body changes. The front end becomes an attachment device. Hooks or horn-like outgrowths dig in. The parasite buries itself partly into the musculature or skin. The rest of the body may hang outside like a grim little banner, announcing that private property laws have once again failed to protect the resident. There are species known to infect deep water fish and sharks by embedding these anchoring structures into skin, muscle, or around the bases of fins. Once lodged, they feed on tissue fluids, blood, or damaged tissue. The wound itself can remain open and inflamed. Secondary infections may follow. The host does not just lose nutrients to the parasite, it also pays the cost of carrying a persistent lesion in a place where healing may be slow and immune defense expensive. The anchor does exactly what it is meant to do. It turns the host body into a mounting point. If that sounds unpleasant, gill parasites manage to make it worse by choosing a location that is both efficient and difficult to defend. Gills are delicate, well supplied with blood, and constantly washed by water. From a parasite's point of view, this is excellent real estate. From the fish's point of view, it is like discovering that someone has moved into your ventilation system and is billing you for the privilege. Parasitic copepods that settle on gills often use claws, hooked limbs, or suction-like grips to hold themselves in place among the filaments. They can erode tissue, reduce respiratory efficiency, and create inflammation in exactly the organ system the fish can least afford to compromise. In deep-sea species, where oxygen can already be variable and energy budgets are tight, damage to the gills is no small inconvenience. A fish that cannot exchange gases efficiently tires sooner. It may swim less effectively, hunt less effectively, and avoid predators less effectively. Once again, the parasite does not need dramatic violence. It only needs to interfere with a system that the host depends on every second. Then there are the isopods, which bring a different kind of commitment to the job. Marine parasitic isopods are crustaceans too, but they tend to look more like small armoured invaders than subtle infiltrators. Their bodies are flattened, their limbs are strong, their mouth parts are built for clamping, rasping and feeding. Some live in gill chambers, some attach externally, some occupy mouths in ways that have made them famous, or infamous, far beyond marine biology circles. The best known example is the tongue-replacing isopod, which has achieved a level of public notoriety that most parasites can only dream of. It enters through the gills, settles in the mouth, feeds on blood from the tongue until the tongue atrophies, and then remains attached where the tongue used to be, effectively becoming a functional replacement. The fish continues to use the parasite as a kind of living prosthetic. It is one of those facts that sounds so theatrical people assume it must be exaggerated, but it is real. Now that particular case is not the defining image of the deep sea alone, but it tells us something important about marine parasitic design. If a mouth offers shelter, access to blood, and constant passage of food and water, then a parasite will treat it as a viable address. And when an isopod chooses that address, it arrives well equipped. Hooked legs dig into tissue. Body shape helps wedge it firmly in place. Mouth parts rasp and feed. The host cannot easily remove it because the parasite is inside, braced and adapted to exactly that environment. The fish carries on because it must. Life in the ocean does not pause for existential crises. If your tongue has been replaced by a crustacean tenant, you continue being a fish as best you can. Other parasitic isopods live in gill chambers or cling to skin. Their hooked periopods, the walking limbs modified into gripping tools, allow them to attach tightly enough that current and host movement are not enough to shake them loose. Some feed on blood, Others take mucus or tissue. Many cause chronic damage, and because they are relatively large compared to many other parasites, their impact is hard to ignore. A fish with a large isopod in its gill chamber is carrying a visible burden, one that interferes mechanically while also draining resources. In darker offshore and deeper environments, where host encounters can be limited, that sort of secure occupation is a sound strategy. Distasteful? Yes. Efficient? Absolutely. Worms bring their own equipment to this contest. Parasitic nematodes, cestodes, and trematodes each solve the problem of attachment differently, and all of them do so with the sort of dedication that makes one appreciate the polite boundaries maintained by most furniture. Nematodes often use teeth, cutting plates, or muscular mouths to bite into tissues or hold position in the digestive tract. Some embed in stomach walls or other organs, where they can cause inflammation, ulcers, or cyst-like lesions. Their bodies are slender and durable, often protected by a tough outer cuticle. They do not need to look dramatic to be effective. They simply need to survive digestive chemistry, maintain position, and keep feeding. Cestodes, or tapeworms, are in some ways even more impressive in their shamelessness. They have no interest in developing a complicated face, when a scolex, the attachment structure at the front end, will do. That scolex may carry suckers, hooks, grooves, or bothria, which are elongated attachment slots that clamp against intestinal tissue. In sharks, rays, and many marine fishes, tapeworms can be abundant, including in deep-water hosts. Some species have extraordinarily elaborate head structures, bristling with hooks or armed with extendable tentacles used to secure themselves in the gut. Once fixed, the rest of the body grows into a chain of reproductive segments, each essentially a packet of future parasites waiting to be released. If ever there were a life strategy built on ruthless efficiency and absolutely no concern for aesthetics, this would be it. The deep sea is particularly good territory for parasites with such methods, because many of the larger predators there swallow prey whole or in big pieces. That means parasites lodged in one host have repeated opportunities to move into the gut of another. A larval cestode in a small fish may end up in a larger predator, attach with its hooks or grooves, and begin maturing in a system already processing a protein-rich meal. It is difficult not to admire the timing, though admiration should be understood here as the sort one gives a safecracker while checking that all one's doors are locked. Trematodes often use suckers, sometimes one around the mouth and another on the body, to maintain position in the tissues or digestive tract of hosts. Their bodies are flat, which helps in close spaces, and their attachment is not merely mechanical but aided by muscular control and the simple advantage of being exactly where the host would prefer not to have anything extra. They may not look fierce in the way a toothed isopod does, but that is only because flatworms have a gift for understatement. Their ability to stay put and continue feeding through changing conditions is the point. Then there are the thorny-headed worms or acanthocephalans, which deserve special mention because they seem to have taken the assignment a little too literally. Their defining feature is an aversible proboscis armed with hooks. When the parasite is ready to attach, this spiny structure is extended and embedded into the intestinal wall of the host. It is in effect a biological grappling device. Once anchored, the worm absorbs nutrients across its body surface while remaining fixed in place by that hooked proboscis. In fish and marine mammals, including species associated with deeper waters, these worms can cause substantial tissue damage. The host's gut wall may become inflamed or perforated. The parasite, meanwhile, remains attached with the calm confidence of something that brought exactly the right tool. Attachment in the deep ocean is not only about resisting motion, it is also about dealing with the host's defences. Skin is slippery, mucus contains immune factors, tissues may swell or attempt to isolate the invader. A good parasite answers these challenges with form and chemistry together. Hooks do the first part, secretions do the second. Many external parasites release substances that help them stay embedded, reduce immediate host reactions, or break down local tissue just enough to make feeding easier. It is not enough to cling. You have to cling in a way that turns resistance into manageable inconvenience. Some deep-sea parasites go further and sink parts of themselves into the host, while leaving other parts outside. This is a very practical arrangement. The embedded section anchors the animal securely and accesses blood or tissue fluids. The exposed section can handle reproduction, release larvae, or simply take up space in a way that would be embarrassing if the host had any effective way to file a complaint. Certain spheroid copepods are known for this kind of body plan, with deeply rooted head regions and long trailing bodies outside the host. The damage can be extensive, muscles are pierced, tissue is distorted, swimming may be impaired, yet the parasite persists because its hold is deep, literal and difficult to challenge. The mouth, of course, remains one of the most unsettling sites of occupation because it is so intimate and so important. A parasite in the mouth is not merely on the host, it is in the root of feeding, breathing, and basic contact with the world. Mouth-dwelling parasites benefit from regular water flow, access to tissue, and protection from outside forces. The host cannot easily scrape them off without damaging itself further. Some crustacean parasites clamp onto oral tissues with hooked legs and stay there, feeding and occupying space that should belong to the animal's own anatomy. Others may lodge near the jaw or palate, even when they do not fully replace a body part in the dramatic fashion of a tongue-replacing isopod. They still transform the mouth into a contested structure. It helps to remember that in the abyss, useful shelter is not abundant. A mouth chamber, a gill chamber, a fold of skin, the base of a fin, the lining of a gut. These are stable environments compared to the open water. They come with nutrients and some protection. Natural selection has therefore produced parasites exquisitely tuned to each of these places. Their teeth are not random, their hooks are not decorative, their clamp-like mouth parts are not over-designed. They are the result of repeated filtering through one very harsh question. Did you hold on long enough to survive and reproduce? If the answer was yes, the design continued. This is also why so many parasitic body forms look, to human eyes, exaggerated or grotesque. We are judging them against the expectations we have for free-living animals. Symmetry, mobility, recognizable limbs, faces that seem to make sense. Parasites are under different instructions. Once feeding and reproduction depend mainly on secure attachment, other features may shrink, twist, or vanish. Locomotion can become less important than anchorage. Streamlining becomes irrelevant if you no longer need to move much after settling. Reproductive tissue may expand enormously because once a host has been secured, the safest plan is often to produce as many offspring as possible and let the water carry them toward the next disaster. Among deep-sea fishes, especially those already scarred by hard living, it is not unusual for parasites to be found attached around the head, mouth, fin bases and gills, because these regions offer access, blood supply and purchase. A parasite buried near the jaw may interfere with feeding. One on the gills may reduce breathing efficiency. One attached near sensory organs may alter how the host navigates. Even when the parasite is small relative to the fish, the position matters. Placement can turn a modest feeder into a serious burden. The host naturally is not entirely helpless. Fish may produce mucus, shake, scrape, bite, or rely on immune defences. Some species may avoid heavily infected areas or hosts. Cleaner organisms in shallower waters remove external parasites, though this service becomes less available in many deep habitats. But in the abyss, where encounters are limited and opportunities for maintenance are fewer, parasites with strong attachment structures often gain the upper hand. A fish in darkness cannot simply schedule a quick grooming appointment and move on. It endures what it carries, and that endurance is part of the horror, if we're honest. Many of these relationships are not brief assaults, they're extended occupations. The parasite digs in, feeds steadily, grows mates, releases offspring and remains while the host continues swimming through the cold. No music swells, no narrator from within the fish delivers a dramatic monologue about betrayal. There is just function. The host breathes, the parasite holds, water moves through the dark. Over time, all that holding on leaves its mark. Tissue thickens or erodes. Blood is lost, mouths deform, muscles waste. Openings meant for breathing become crowded. Skin becomes a site of chronic damage instead of protection. Even a host that survives is often changed by what clings to it. And that is before we even consider the parasites that do not stay politely on the outside or at the surface of an organ, but move farther in, where hooks and teeth give way to a different kind of occupation altogether, one that works more slowly and from deeper inside the flesh. And once a parasite has learned how to hold on, the next improvement is obvious. Why remain on the surface if the safest meal is deeper in? Why cling to the outside of a host if you can move past skin, past gills, past the first line of defence, and settle inside the tissues themselves, where the body becomes both shelter and pantry? This is where deep-sea parasitism stops looking like infestation in the casual sense and starts looking like occupation. Not a quick attack, not a single wound. A long arrangement, carried under the skin, within the gut wall, around the organs, inside the muscle, sometimes for months or years, while the host goes on swimming through darkness with a passenger it cannot easily dislodge. Deep-sea fishes commonly carry both external and internal parasites, and older work summarised in NOAA's Marine Pathology volume notes that deep-sea fish are often infected primarily by larval nematodes and cestodes, rather than by large numbers of adult helminths. That detail matters because larval parasites are often the quietest kind. They are not yet in the final host they need for reproduction, so they are built to wait. A shark, a ray, a marine mammal, a larger predatory fish, something still has to eat the current host before the parasite reaches the next phase. Until then, it remains inside, developing slowly, encysted or coiled in tissue, drawing what it can, damaging what it must, and asking only that the host remain alive long enough to be useful. It is a remarkably cold strategy. The host is not just food, it is storage, it is transport, it is the middle page in a longer plan. And because the deep ocean is full of food webs built on swallowing prey whole or in large pieces, that sort of waiting game works very well. NOAA's Broader Symbiont Guide notes exactly this kind of multi-host logic, where a single parasite species may use different life stages in a shrimp, a fish, and a bird or marine mammal. Among the most familiar internal marine parasites are anisakid nematodes, the round worms that show up again and again in ocean food webs. They are not limited to the deep sea, but they are common in marine and anadromous fishes and are part of the same predation chains that reach into deep water. In fish, larval anisakids are found in the flesh and viscera. An official fish disease guidance from Alaska notes common genera such as Anisakis, Pseudoterra nova, and Contracaicum in those body compartments. ANO, a technical report on Anisakis in fish, likewise reported larvae on mesenteries and internal organs, with occasional occurrence in muscle tissue, and noted fibrous encapsulation and adhesions around larvae in heavily infected fish. That is the kind of damage that does not look dramatic at first glance. No sudden collapse, no obvious external spectacle, just a host carrying coils of foreign tissue through its body cavity while scar tissue slowly forms around them. There is something especially grim about the way these worms use the host's own repair response. The fish recognises that something is wrong and begins walling the intruder off. Fibrous capsules form, adhesions develop, tissues thicken. In a mild infection, the host may continue with a little obvious change beyond the hidden burden. In a heavier one, those repeated little battles add up. Internal surfaces become crowded. Organs may be tethered by inflammatory tissue. Normal flexibility in the body cavity is reduced. The host has not been torn apart in one event. It has been slowly made less efficient from the inside. And in the deep sea, where many fishes live on narrow energy margins already, less efficient can be a very expensive condition. Even Alaska's Fish Disease Handbook while calling many anisakid larvae relatively non-pathogenic to fish, still points to visceral adhesions caused by migrating larvae, which is a polite way of saying the body has been left with internal damage it did not order. The real effectiveness of anisakid worms is that they do not need to finish the job in the fish. In many cases, the fish is only the waiting room. The larva enters after the fish eats infected copepods, or prey fish, then remains in tissues until the fish itself is swallowed by the next predator. That means the parasite is selected not for dramatic killing power at this stage, but for endurance and placement. It needs to remain alive, infective, and difficult to eliminate. A fish carrying larvae in its mesenteries, gut wall, or musculature is not just infected. It is being kept ready for someone else's meal. The CDC notes that anisakid infections are part of marine fish food chains, and multiple reviews point to their presence in both flesh and visceral organs of wild fish. In narrative terms, they are not assassins. They are patient hitchhikers with excellent timing and no concern whatsoever for the comfort of the vehicle. Deep-sea fish are also frequently used by larval cestodes, especially trypanorinch tapeworms, which might sound like the sort of word one invents to win a spelling contest no one wants to attend. But these are real and widespread marine parasites, and their larval stages are often found in the musculature or body cavity of fish. The NOA A pathology volume specifically notes that larval cestodes such as Grillotia are common in deep-sea associated fish, and more recent studies describe trypanorinch cestodes as frequent parasites of marine fish mussels. That location is important. Muscle is not incidental tissue. It is movement. It is escape. It is feeding. It is everything a fish does when it needs to keep itself alive in a place where wasted effort can be fatal. A parasite occupying muscle may not always kill quickly, but it can interfere with body condition, tissue integrity, and the basic quality of movement on which survival depends. Trypanorinch larvae are especially unsettling because they are often heavily armed at the front end, with reversible tentacles or attachment structures covered in hooks. In the fish host, they may sit as plerocercoid larvae in the musculature, waiting for the right predator, usually a shark or ray, to eat the infected fish so the tapeworm can mature in the final host's intestine. Until then, the fish carries those encysted or embedded stages in its flesh, like biological stowaways with legal documents already prepared for the next jurisdiction. Studies on marine fish muscle infections by trypanorinchs describe lesions and tissue reactions, and they repeatedly show how common these parasites are in edible marine fish species. What the host experiences is a long period of occupation, not a clean wound that heals, but a continuing presence in working tissue, exactly where the body can least afford to lose efficiency. Then there are the acanthocephalans, the thorny-headed worms which solve the problem of living inside a host with impressive rudeness. These parasites use a hooked proboscis to anchor into the intestinal wall. Some species attach only superficially and cause relatively mild local damage. Others penetrate much more deeply, and a recent review notes that the attachment organ of some acanthocephalans may penetrate deeply into the fish intestinal wall and trigger severe pathological reactions. The same source describes energy depletion in heavily infected fish, including lowered liver weight in Atlantic cod under high worm burdens. That is worth lingering on for a moment. A parasite fixed in the gut is not just stealing nutrients from food that has already been captured and swallowed. It is also forcing the host to absorb the cost of inflammation, encapsulation, and reduced energy status at the same time. This is theft with paperwork, damage, and recurring service fees. And acanthocephalans do not always remain politely in the intestinal lining. Juvenile stages of some marine species move into other internal compartments of fish, including the gut wall, peritoneum, mesenteries, and body cavity, where they become encapsulated and wait for a seal or whale to eat the fish. That means the host may carry them not only in the digestive tract but in surrounding tissues as well, with cellular reactions forming around the parasite while it remains viable. A recent review on fish acanthocephalans describes exactly that route. from infected crustacean to fish paratenic host to marine mammal final host. For the fish, this can mean chronic internal occupation by hook-bearing juveniles that are not even trying to mature there. They are simply using the fish as a storage stage. The host, once again, becomes a living bridge. Perhaps the most quietly unpleasant of the internal muscle parasites are the myxozoans of the genus Kudoa. These are not worms at all, and they prove rather effectively that the ocean has many ways to make flesh less trustworthy. Alaska's official fish disease guide explains that many Kudoa species infect skeletal muscle, forming pseudocysts packed with spores. It also notes that high intensities can produce post-mortem myolique faction, the so-called soft flesh syndrome, because the parasite releases proteolytic enzymes that break down the muscle. In practical terms, the fish may look intact, only for the fillet to soften, degrade, or become almost jelly-like after death. Now, from the host point of view, this is not always the fastest killer while alive, and the same guide notes that Kudoa is often tolerated without reported fish mortality. But that does not make it benign. It means the parasite is another example of the slow strategy, one that uses living muscle as habitat and alters tissue from within, rather than through dramatic immediate disease. What makes Kudoa especially interesting in this darker parade is that it reminds us deadly is not always about instant death. Sometimes the danger is the long undermining of the very tissues that define what a fish can do. Skeletal muscle is propulsion, feeding strikes, posture in the water column, migration, escape, and stamina. A parasite that develops inside muscle fibers, forms pseudocysts, and leaves inflammatory changes behind is taking up residence in the machinery of survival itself. The Alaska Guide also notes that some Kudoa species parasitize heart muscle, where they may negatively affect cardiac performance. That is a remarkable sort of trespass. Not content with occupying flesh used for movement, some of these organisms extend the strategy into the muscle that keeps the entire circulatory system going. Slow killers rarely announce themselves. They choose important tissues and wait. This is one of the reasons internal parasites can be so ecologically important even when they are not causing spectacular outbreaks. They alter host condition gradually. They reduce growth. They drain nutrients. They scar tissues. They compromise digestion, movement or respiration by attacking the structures that support those functions. NOAA's deep-sea parasitism feature emphasizes that internal parasites are common in deep-sea fishes, and that parasites can alter host behavior and affect ecological communities. When the damage is internal, that influence may remain hidden from us while still being very real for the host. A fish may feed less effectively because worms occupy its gut or body cavity. It may swim less well because larval cestodes or myxozoans occupy muscle. It may survive, but survival in poorer condition is not the same as health. In a place where food is scarce and every movement costs, a slow reduction in efficiency can be a serious sentence. And this, I think, is what makes the internal feeders so unnerving in a different way from the hook-faced external ones. A parasite on the outside at least declares itself. You can point to it. You can say, with some authority, there is the problem, attached to the skin like a terrible design choice. But an internal parasite can leave the host looking almost normal from a distance while the real damage builds under the surface. Encysted larvae on the mesenteries, worms embedded in the gut wall, juvenile acanthocephalans waiting in the body cavity, pseudocysts inside the muscle. A fish may still be swimming through black water, still hunting, still avoiding things with larger teeth, and all the while parts of its body are serving someone else's life cycle. It is a very quiet kind of predation, the sort that keeps the host alive because a living host remains useful longer. There is, naturally, a certain deep-sea practicality to all of this. Food is unreliable, encounters are uncertain, so parasites that can enter tissue, endure there, and wait for the right predator have solved the problem in a way the abyss respects. They do not waste effort on speed. They do not spend energy building dramatic weaponry for open pursuit. They let other animals do the swimming, the feeding, and eventually the swallowing. The host lives with the burden until a larger mouth closes around it, and the parasite continues its schedule. It is economical in the worst possible sense, and once you notice how much of this hidden damage depends on access to tissue and body fluids, the next step in the descent becomes difficult to avoid, because some parasites do not settle for flesh alone. They move one layer closer to the supply itself, and begin taking the thing the host can lose least comfortably in a dark ocean already full of mouths. And once a parasite begins feeding on the tissues beneath the skin, the next step is almost inevitable. Go closer to the supply itself. Do not settle for damaged flesh or leaking fluid when the host is already carrying a rich, warm, circulating meal through every important part of the body. Blood is transportable nutrition. It moves where the host moves. It reaches the organs that matter most. And in the ocean, blood feeding has evolved again and again in very different groups, including marine leeches, parasitic isopods, and parasitic copepods, which tells you something rather grim about how useful the strategy is. Once evolution finds a way to drink directly from a living animal, without killing it too quickly, it tends to keep that arrangement. The deeper water gets, the more sensible that strategy becomes. In the deep sea, external parasites are not a curiosity or a rare accident. They occur across a broad range of habitats and depths. One study based on ROV observations off the northeastern United States examined fishes from 494 to 4,689 metres and found ectoparasitic copepods and isopods on multiple deep-sea host species, with gnathid isopods still showing up down to 3,260 metres. The authors concluded that ectoparasitism is a significant part of deep-sea biodiversity, which is a very clinical way of saying that even in black water, things are still being sat on, pierced, and fed from. Blood feeding also requires a special sort of biological audacity. The host does not simply offer up an artery and wish the parasite good luck. Blood clots, wounds close, tissues swell, so marine blood feeders have had to evolve ways around those obstacles. Reviews of blood-feeding animals note that inhibiting hemostasis, the body's clotting response, is one of the major innovations required for this lifestyle. And isopod reviews have specifically noted anticoagulants in symathoid parasites. In other words, these animals do not just bite. They arrive chemically prepared. They pierce, hold on, and interfere with the host's attempts to stop the leak. That is not dramatic flair. It is what makes the meal possible. Among the most persistent of these marine blood feeders are the gnathid isopods, which are often called the ticks of the sea, and unfortunately the comparison is deserved. They are temporary parasites rather than permanent residents. Their juvenile stages attach to fish, feed on blood and fluids, then drop away to the seabed to digest before seeking another meal. What makes them especially relevant here is their range. Studies describe gnathids as marine hematophagus parasites, living from the intertidal to the abyss, and deep-sea observations show they are the ectoparasites most consistently seen across a broad depth range. If you are hoping the abyss might at least be free of sea ticks, I am afraid the news is poor. That temporary style is worth pausing over because it gives gnathids a strange sort of efficiency. They do not necessarily stay fixed to one host for life. They use the host like a refill station. A juvenile gnatid attaches, swells visibly with blood, and then leaves to digest and molt elsewhere. Another stage returns later for another blood meal. It is less like moving into a house, and more like repeated armed burglary committed by something the size of a particularly determined crumb. Research on gnathids notes that they parasitize fish only during their juvenile phases, while adults are non-feeding, which means the whole purpose of the parasitic period is to acquire enough blood to continue development. Blood is not just food here, it is a ladder to the next body form. For the fish, the cost is not simply the volume of blood removed in one bite. It is the wounds, the stress, and the cumulative burden. Gnathids are also important because they can act as vectors, carrying blood parasites among fish hosts. Reviews of their ecology describe them not just as consumers and prey, but as vectors with multiple ecological impacts. That makes them closer to marine mosquitoes than to simple scavengers. The difference, of course, is that mosquitoes generally spare us the insult of living all the way down to abyssal depths. Nepheids did not feel the need to be so considerate. Then there are the Egids, another group of isopods that seem to have looked at the problem of marine feeding and decided that ambush blood theft was a respectable profession. A broad isopod review states very plainly that Aegids are micropredators of fish, taking a blood meal and generally not staying on the host. They are not permanent tenants in the way some other parasites are. They are more like hit-and-run specialists. In the deep-sea North Atlantic ROV survey, Aegids were among the isopod families recorded on deep-sea fishes, which means this style of feeding is not confined to bright coastal water. It persists where the sea is dark, cold, and already short on spare energy. There is something especially unpleasant about temporary blood feeders, because they do not have to commit to the host in order to do damage. A permanent parasite at least has an interest in keeping its address functional. A temporary one can arrive, take a concentrated meal, and leave the host with open wounds, blood loss, and the risk of secondary infection. Isopod reviews note that fish parasitic forms feed on blood or wound ooze, and that their attachment with mouth parts and periopods can create openings that allow microbial disease to enter. So the feeding event is not only theft, it is also a breach. A fish does not just lose blood, it loses the integrity of the skin or gill surface that was supposed to keep the outside world outside. Some blood-feeding isopods do stay much longer, and the cymothoids are the classic example. These are obligate parasites of fishes, often found on the skin, in the mouth, or in the gill chambers. The same PLOS review notes that most cymothoids feed on the blood and tissue of their hosts, and that cymothoids live on external surfaces or in buccal and gill cavities and possess anticoagulants. That is already bad enough, but cymothoids have a further talent for choosing places where blood flow is good and removal is difficult. Mouths, gills, soft tissue folds, these are not random selections. They are strategic locations where feeding can continue while the host struggles to carry on with normal life. The most famous cymothoid is the tongue-replacing isopod, which has become so well known, partly because it sounds like the sort of lie a fisherman tells when he wants everyone else to leave the boat. But it is real. Smithsonian's overview explains that the isopod severs the host fish's tongue, latches onto the remaining stub with hooked appendages, then lives in the vacated space while feeding on the host's blood. The fish continues using the parasite as a functional replacement. That is a disturbing enough arrangement in shallow water. In darker offshore habitats, the same basic lesson applies even where the specific species differ. A blood feeder does not always need to sit on the outside where the host can scrape at it. Sometimes it chooses the mouth itself and lets the fish keep swallowing around the problem. Copepods, meanwhile, handle blood feeding with a different style. Many parasitic copepods are less immediately dramatic in appearance than the isopods, but the damage they do can be extensive. NOAA's technical report on marine fish pathology notes that parasitic copepods can penetrate organs and blood vessels, cause hemorrhages, alter fish blood composition, and, when mature, are associated in some cases with reductions in fish weight, fat content, and hemoglobin. That is a very tidy summary of a very untidy biological relationship. A blood-feeding copepod does not need to look impressive. It only needs to remain anchored and keep tapping the host's circulation long enough for the host's condition to slide. Deepwater copepods make this especially clear. The ROV survey in the western North Atlantic recorded copepods from the families Lernaeopodidae and Spheriidae on deep-sea fishes across nearly 5 kilometers of depth range, and a 2024 record from Japan documented the Spherid Laphura cornuta on a deep-sea eel caught at 550 and 620 meters on the continental slope. Spherids are mesoparasites, meaning they are often partly embedded in host tissue rather than merely clinging to the outside. That matters because once part of the body is buried near the blood supply, feeding becomes secure and removal becomes difficult. A fish can flee a predator. It cannot easily outrun something already rooted in its flesh. This is one of the strange practical advantages of blood feeding in the deep sea. A parasite does not need to consume large chunks of muscle to have a serious effect. Blood is compact, portable energy. It also carries iron, proteins, and all the products of the host's own feeding effort. The host has already done the expensive work of finding food in an environment where food may be scarce. The parasite simply inserts itself into the supply chain. That is why blood feeding can be so effective in black water. It bypasses the hard part. Instead of chasing a meal through darkness, the parasite rides on an animal that already knows how to locate one, then skims off the converted result. The host is the hunter, the parasite is the tax collector. Leeches belong in this darker procession as well, even if many of the best studied marine examples come from sharks, rays, and coastal or shelf settings rather than the abyss proper. Marine obligate blood feeders include fish specialist and elasmobranch specialist leeches, and studies on marine passicillid leeches show that they can cause epidermal disruption and blood loss. In one recent life cycle study of Branchelion lobata, even a single leech provoked a host immune response, while heavy infections in captive rays were associated with lethargy, poor feeding, and in one case, death. That does not mean every leech encounter is quickly fatal. It means the cost of repeated blood loss and tissue damage can become serious, especially when the host is already living under narrow physiological limits. Marine leeches also underline a useful point about blood feeding. To drink blood successfully, a parasite has to keep the host's blood from clotting, and often has to dull or outlast host defences. Studies on marine leech anticoagulants emphasise exactly that, and broader work on blood-feeding animals notes the central role of salivary compounds that interfere with clotting. This is part of what makes blood feeders such effective long-term parasites. They're not just thieves with a sharp mouth. They are biochemists, however unintentionally. They arrive carrying tools that turn a wound into a tap. There is another reason blood feeders are so successful in the ocean. They do not always need the host to die. In fact, many of them are better off if it does not. The tongue-biting cymothoid lets the fish continue normal activity while feeding on blood. Egids often take a meal and depart. Gnathids feed temporarily, drop off, digest, then return at another stage. Leeches can detach and feed again. This means the host is not always treated as a one-time meal, but as a living landscape to be revisited, exploited, or maintained at a useful level of weakness. From the parasite's perspective, killing too fast is poor planning. From the host's perspective, surviving the encounter is not the same as escaping the problem. And in the deep sea, that slow burden matters more than it might in richer environments. NOAA's pathology review points out that parasitic copepods influence host growth, condition, reproductive systems, and the broader productivity of aquatic systems. The report also notes blood alterations, organ damage, hemorrhage, and declines in body condition under some infestations. That is the real power of blood feeders in black water. They exploit animals that often cannot afford the loss. A shallow water fish in a productive system may have more chances to recover. A deep-sea fish living where meals are infrequent and movement is expensive may not. A small drain repeated over time becomes a serious subtraction. There is also a hidden technical problem in living on blood alone. Blood is nutritious, but it is not a complete and effortless diet. Recent work on marine obligate blood feeders found persistent bacterial associations and low diversity microbiomes in blood-feeding leeches, isopods, and a blood-feeding copepod, suggesting that symbiotic microbes likely help these parasites manage the nutritional and physiological challenges of this lifestyle. That is one more layer of efficiency to admire from a safe emotional distance. The parasite does not merely bite and swallow. In some cases, it brings microbial help to make the meal workable. Even the blood thief, it seems, may need a small staff. What all of this adds up to is a feeding strategy that fits the deep ocean almost too well. Blood feeders do not have to wait for carrion to fall. They do not have to outswim every meal. They do not have to gamble everything on a single chase in the dark. They attach, pierce, suppress clotting, and take what the host has already collected. Some leave, some remain, some return. And because many deep-sea fishes are already stretched thin by cold, depth and scarce food, even a parasite that seems small can become a serious burden once it starts drinking directly from the moving supply. Still, for some parasites, even blood is not the final answer. A meal can keep you alive, but a body can do more than that. A body can shelter you, move you, mature you, and in some cases become the place where your entire life cycle changes direction. And that is where the next set of creatures becomes even stranger, because some of the deadliest deep-sea parasites do not just feed from a host for a while, they borrow the host itself as if it were equipment. And that is where the strategy becomes even colder, because some parasites do not simply take a meal from a host and move on. They borrow the host's body the way a careful thief borrows a house, a car, and the keys all at once. The host becomes transport, shelter, storage, and timing device. In marine parasitology, that often means intermediate or paratenic hosts, animals that carry larval stages until a larger predator eats them, allowing the parasite to continue its development. Fish and squid are especially important in these marine life cycles, serving as way stations for parasites whose final destination is often a shark, ray, seal, whale, dolphin, or seabird. That distinction matters because a parasite using a borrowed body does not need the current host to be its final home. It only needs that host to stay alive, swim normally enough, and eventually end up in the mouth of something larger. The host is not the conclusion, it is the bridge. That is one reason so many marine parasites favour tissues like the body cavity, viscera, muscle, and mesenteries. Those places let them remain protected and infective while the host keeps moving through the food web. The host thinks it is simply feeding, migrating, or surviving another day. The parasite is using the same body as temporary housing while waiting for the next transfer. Anisakid nematodes are among the clearest examples of this borrowed body strategy. Their life cycle typically begins with eggs released by adult worms in marine mammal hosts. Small crustaceans consume the early stages, and fish or squid then eat those crustaceans. Once inside fish or squid, the larvae do not mature into adults there. Instead, they persist as infective larval stages until the host is eaten by a marine mammal. Reviews and public health references describe fish and squid as intermediate or paratenic hosts in this cycle. And NOAA's overview notes that Anisakis larvae can pass from small crustaceans into fish or squid, encyst there, and await trophic transmission to cetacean definitive hosts. There is a particularly bleak elegance in that arrangement. A fish may spend weeks or months foraging through cold water, gathering energy one difficult meal at a time, and all the while it is carrying a parasite that has no intention of finishing its life there. The larva is not investing in the fish as a long-term home. It is using the fish as a sealed container that can swim, avoid being digested by the wrong species for a while, and eventually present itself to the right predator. That is what a paratenic host really is in practice. It is a body on loan, a living envelope, and the parasite's real success lies not in what it does to the fish immediately, but in whether the fish is eaten on schedule by something higher in the chain. The deep ocean makes this strategy especially useful because so many of its food webs depend on swallowing prey whole or in large pieces. Squid eat crustaceans, fish eat squid. Larger fish eat smaller fish. Sharks and marine mammals take the larger ones. That means a parasite embedded in one host can move upward through repeated predation without having to solve the problem of locomotion for itself. It lets the borrowed body do all of that. Even official disease and review documents describe fish and cephalopods as transport or paratenic hosts for anisakids, keeping larvae infective until they reach the final host. The parasite is not in a rush. The host does the travelling. A related and equally unpleasant example appears in the thorny-headed worms, particularly marine acanthocephalans such as Bulbosoma and Coronosoma. Reviews note that their larvae or juveniles occur in various body compartments of fish, serving as paratenic hosts. while the adults live attached to the gastrointestinal mucosa of marine mammals such as whales and seals. Their eggs leave the mammal with feces, are taken up by small crustaceans, and then reach fish when those crustaceans are eaten. Once again, the fish is not the final address. It is the borrowed body in which the parasite waits for a marine mammal to complete the next step. That waiting can happen in multiple parts of the fish, which is what makes it feel less like a simple infection and more like warehousing. The review from the University of Copenhagen portal states plainly that these larval or juvenile acanthocephalans occur in various body compartments of fish paratenic hosts, while awaiting predation by marine mammals. In other words, the host's internal anatomy becomes temporary storage infrastructure. A fish that appears intact from the outside may already be carrying parasites whose only long-term plan is to be carried upward into a whale or seal. It is not hard to see why this counts as body borrowing in the strictest sense. The host is doing the swimming, the parasite is doing the waiting. Trypanoranch tapeworms push this borrowed host logic into deeper water with particular efficiency. A 2023 deep-sea research. Part 1 study examined larval Grillotia infections in the deepwater lantern shark Edmoptera spinax, a bentopelagic shark occurring from roughly 70 to 2,000 metres, usually around 200 to 500 metres. The study identifies E. spinax as one of the parasite's paratenic hosts, and notes that pelagic and demersal sharks, rays and skates, are definitive hosts of Grillotia species. That means even a deepwater shark can function as borrowed transit space for a tapeworm whose real reproductive future lies in a larger elasmobranch. The host may itself be a predator in the dim sea, but to the parasite it is still just another vehicle. The details are wonderfully grim. In that same study, larval Grillotia pleurocertae were reported mostly from the tail muscle close to the vertebrae, and the authors note that Grillotia pleurocertae are rather euryxenous, meaning many fish species can serve as intermediate or paratenic hosts. That is a broad and effective strategy. The parasite does not rely on one exact host species every time. It borrows whichever suitable bodies are available in the network until one of them ends up inside the correct definitive host. The fish or shark becomes part of a long conveyor belt of flesh through the deep ocean, and the parasite rides that belt from one body to the next. There is something almost insulting about the scale of that opportunism. We tend to imagine top predators as the final authority in their environment. Yet here is a deep-water shark, bioluminescent, capable, adapted to life hundreds of meters below the surface, and even it may be reduced to a borrowed compartment in a tapeworm's larger plan. The parasite does not particularly care that the host is a shark. It cares that the shark can be eaten, or at least can pass the larva farther through a food web involving elasmobranchs. Borrowed is borrowed. Status in the ecosystem does not grant immunity from becoming someone else's transport. If borrowed bodies sound impersonal in these trophic parasites, rhizocephalan barnacles make the concept far more intimate. These are parasitic barnacles that infect crustaceans, and by adulthood they no longer resemble ordinary barnacles in any comfortable sense. Taxonomic and developmental sources describe them as parasites of crustaceans with an initial completely internal phase. The adult female consists of an internal, ramifying, nutrient-absorbing root system and an external sac called the externa that houses the reproductive organs. During the internal phase, the parasite develops a root-like interna that infiltrates host tissues and absorbs nutrients from the host. This is not merely feeding on a borrowed body, it is replumbing one. The way rhizocephalans get in is impressively invasive. Frontier's review of Polyascus planus explains that after the female cypress larva settles on a decapod host, parasitic tissue is introduced into the host, either through penetration of the cyprid tenniel or, in kentrogonid forms, via a hollow, stylet-like structure. Once inoculated, the parasite develops inside the host into an epithelium-enclosed stage, and then into the ramifying interna. Eventually the externa emerges on the host's abdomen, while remaining connected to the internal root system by a stalk. So the crab or shrimp does not merely carry the parasite on the outside, Its body cavity becomes the parasite's infrastructure, and its tissues are literally infiltrated by the parasite's feeding network. Rhizocephalans are perhaps the most literal body borrowers in the ocean, because they have abandoned the ordinary crustacean digestive plan almost entirely. The OUP taxonomy paper notes that all stages of these parasites lack any trace of an alimentary canal. Instead, the parasite relies on the internal root system to absorb nutrients from the host, while the externa functions as the reproductive organ. In simple terms, it no longer bothers to maintain a normal way of eating, because it has converted the host into the feeding system. It is difficult to imagine a clearer example of a parasite treating another animal's body as borrowed equipment. It gets stranger. Rhizocephalans do not only use the host's tissues, they also alter host biology and behaviour. The 2024 biology paper states that rhizocephalans can manipulate host metabolism, morphology, and behaviour, with the feminisation of male crabs being one of the most striking examples. It further notes that the interna is responsible for host manipulation, and that specialised invasive rootlets invade the host's nervous ganglia. In other words, the parasite is not content with borrowing the host's nutrients. It extends into the host's control centres and begins influencing the machinery that governs the body it has occupied. That manipulation can become alarmingly practical. A classic behavioural study on Succulina polygenia found that infected shore crabs cleaned the parasite's externa with their claws, and during larval release, adopted the stereotyped larval release behaviour of female crabs, remaining stationary and flexing the abdomen in a waving action to assist the parasite's nauplii. The host was not simply weakened. It was performing parental care on behalf of the parasite. The borrowed body had become a nursery assistant. That is a level of appropriation far beyond feeding. It is one animal conscripting another animal's instincts for reproductive labour. The host's body chemistry can be redirected as well. In the frontier study on Polyascus planus, researchers examined vitellogenin, the precursor of major yolk protein in crustaceans, because rhizocephalans appear to draw on host reproductive resources during the development of the externa. The paper describes how the parasite's life cycle includes host control and host alteration, and it specifically investigated whether the parasite acquires vitellogenin from the host and whether parasitized male hosts are manipulated in that context. Even without overstating the findings, the overall picture is clear. Rhizocephalans do not merely live on a crustacean, they tap into the host's reproductive economy and turn the host body into support machinery for the parasite's own offspring. What makes all of this especially relevant to a descent into darker waters is that rhizocephalans are not confined to tide pools and familiar coastlines. The 2024 biology paper notes that Mycetomorpha abyssalis was recently described from the deep sea near the Japanese coastline, and the group as a whole includes parasites of decapod crustaceans across many marine settings. So even the abyss is not exempt from this way of life. A deep-sea crustacean can become host to a parasite that gives up a normal digestive tract, grows a root system through the body, and turns the animal into a mobile feeding and brooding platform. The darkness does not simplify life. It gives strange strategies more room to persist. There is a common thread running through anisakids, acanthocephalans, trypanarynch tapeworms, and rhizocephalan barnacles, even though they belong to very different branches of life. None of them insist on doing all the hard work themselves. They outsource motion, protection, and often even timing to the host. The borrowed body finds food, avoids threats, circulates nutrients, enters the right habitat, and eventually may place itself in the path of the next predator. The parasite survives not by being the strongest swimmer in the black water, but by becoming a passenger in something that already knows how to survive there. That is one of the reasons these parasites are so successful in the deep ocean. Food is uneven, encounters are uncertain, free-living movement is expensive. Borrowing a body solves nearly all of those problems at once. A larva can sit in muscle, body cavity, or connective tissue while a fish, squid, crab, or shark spends its own energy crossing distances the parasite could never manage alone. The host becomes raft, pantry, armour and delivery system, all while still imagining itself to be in charge of its own life. From the parasite's point of view, it is an ideal arrangement. From the host's point of view, it is a long misunderstanding with terrible consequences. And after enough time inside a borrowed body, some hosts stop looking entirely like themselves. They are still moving, still feeding, still present in the dark water, but parts of them have already been redirected, replaced, hollowed, or occupied. They have not been fully eaten in the dramatic predator-prey sense. They have been used in pieces, slowly and methodically, until what remains is something still alive, but already partly claimed. Still alive, but already partly claimed. That is really the image that lingers once you look closely at enough marine parasites. Not a clean kill, not a predator arriving, taking a bite, and leaving a clear ending behind. Something more awkward than that. A fish still swimming with a mouth no longer fully its own. A crab still moving while an internal root system is spread through its body. A deep-water fish carrying a copepod so deeply embedded that the parasite has reached the liver, the body cavity, even the heart. The host remains in motion, the feeding continues, and from the outside, life goes on just enough to make the arrangement useful. One of the most unsettling things about marine parasitism is that it often leaves the host looking only partly ruined. That sounds almost merciful for a moment, until you remember what it really means. The animal is not spared, it is preserved in working order. Preserved badly perhaps, but still well enough to swim, respire, feed, migrate, brood, or simply remain available. This is especially valuable in the ocean, where a host body can function as transport, shelter, and feeding platform all at once. A parasite that destroys too quickly loses those advantages. A parasite that leaves the host alive but visibly diminished gains much more. The fish with a crustacean where its tongue should be is probably the clearest example of this half-consumed condition. Smithsonian Ocean's summary of cymathoid tongue-biters explains that the parasite severs the host fish's tongue, latches onto the remaining nub with hooked appendages, and then lives in the vacant space while feeding on the host's blood. The fish continues normal activity, which is, I think, one of the most disturbing details. Not because it makes the fish seem unharmed, but because it tells you how good the parasite is at taking over an important space without collapsing the system entirely. The mouth remains functional, but only by incorporating the parasite into the act of feeding. The animal has not been fully eaten, yet a body part has effectively been replaced by something that arrived as an invader. Smithsonian Magazine's longer description puts it in even harsher terms. The isopod enters through the gills, attacks until the tongue shrivels and dies, and then becomes the fish's working tongue. The host, in other words, is still alive and still feeding, but part of its original anatomy has already been removed from the story. This is not just parasitism as nuisance, it is parasitism as partial substitution. The fish remains a fish. It is also now carrying a living prosthetic with its own reproductive agenda. That is what half-consumed can mean in the sea. Not gone, but occupied at a level the host cannot reverse. And the mouth is only one location where this sort of partial takeover happens. In deep and cold waters, parasitic copepods of the family Spheridae and related groups often solve the same problem in a more invasive way. These are mesoparasites, meaning much of the female parasite becomes embedded in the host's tissues, while part of the body remains outside. A South African review of Spherian species notes that these copepods are regarded as mesoparasites of deep-water fishes, and that the female's hammer-shaped cephalothorax is embedded inside the host, while the neck and trunk extend outward. The host, then, is not carrying something merely attached to the skin. It is carrying something rooted into the body wall and muscles, while the exposed portion remains outside, like a sign of internal occupation. That is already unpleasant enough in ordinary muscle. What makes it harder to forget is how far some of these copepods can go. The Antarctic study on bathypelagic Bathylagus antarcticus describes Sarcotretes and Paeonocanthus copepods with cephalothoraxes and necks penetrating deep into the fish's muscles. In the case of Sarcotretes, the cephalothorax was reported to pass through organs and muscles directly into the cavity of the heart. The same study reports deep penetration by Paeonocanthus into the liver, with muscles at the penetration site becoming very loose and the liver slightly deformed. A fish with a parasite in its heart cavity is not simply infected, it is already partly used up as habitat. Vital anatomy has become tunnel, anchor point, and feeding site. Yet the fish is still present in the water, still functioning enough to be caught and studied. It is the looseness of the muscle in that description that stays with me. Not because it is dramatic in a cinematic sense, but because it is so matter-of-fact. The parasite enters, the tissue loses firmness, the organ deforms, the host continues. That is the real character of many marine parasite injuries. They are not theatrical, they are cumulative. The body becomes a little less itself in each occupied region. A fish with a copepod driven into muscle and liver has not yet collapsed, but parts of it are already no longer serving only the fish's interests. The tissue has become shared territory, and in biological terms, shared territory is usually bad news for the original owner. NOAA's Marine Pathology report makes clear that parasitic copepods can do much more than remain superficially attached. It notes that copepods can affect the liver, kidney, spleen, intestines, hypophysis and blood vessels, penetrating into these organs, reducing them and causing hemorrhages. It also notes injury to skeletal structures in some cases and alterations in the blood composition of fish. This is what already half consumed looks like under a more formal vocabulary. Organs reduced, blood altered, hemorrhages opened. Not one fatal strike, but a body gradually transformed into something less capable, while still alive enough to continue serving as host. Deep-sea fishes are especially vulnerable to that sort of long damage, because so many of them are infected primarily by larval stages rather than adult parasites. NOAA's report specifically notes that deep-sea fish are infected primarily by larval nematodes and cestodes, with adult helminths encountered more rarely. That means many deep-water hosts are carrying parasites whose plan is not even to finish life there. The fish becomes storage and transport while larvae sit in tissues, body cavities, or mesenteries awaiting the next predator. A host in that condition is not fully consumed, but it is already partly allocated to someone else's future. This is one reason deep-sea creatures can look intact while being profoundly occupied. The injury is distributed. A fish may have worms in the viscera, larval tapeworms in muscle, a copepod embedded in the flank, and chronic tissue reactions around all of them, yet still be swimming. That outward continuity is what makes the condition so eerie. Predation usually leaves a clear before and after. Internal parasitism often leaves a long middle. The host remains animate while portions of its anatomy are slowly converted into shelter, food reserves, or launch points for the parasite's reproduction. Crustaceans show an even stranger version of this halfway state, when they are infected by rhizocephalan barnacles. These parasites are among the most dramatically modified metazoan parasites known. The 2024 biology paper on Mycetomorpha vancouverensis explains that adult female rhizocephalans consist of two functional parts: an interna, which is a system of rootlets infiltrating the host for feeding and host manipulation, and an externa, which is the reproductive organ. The OUP and molecular studies say much the same thing in plainer terms. Adult rhizocephalans lack normal external feeding structures and rely instead on that internal rootlet system, drawing nutrients from host tissues and even using the host's respiratory and circulatory functions as part of the arrangement. A crab infected by one of these animals is not merely carrying a parasite. Its body has been entered by a branching trophic network that uses it from the inside. That root system matters because it changes what the host is physically. Once established, The crab or other decapod is no longer just an animal with an infection. It is an animal whose internal space is occupied by an additional network devoted to someone else's feeding and reproduction. The parasite's externa may sit outside as a sac full of reproductive tissue, but the real work is done by the interna spreading through the host. The host is still walking, still responding, still technically alive in its own right, yet parts of its interior have become infrastructure for a different organism. There is no cleaner way to describe that than half-consumed. The host has not vanished, but its body has already been repurposed. And the theft does not end with nutrients. Rhizocephalans are also known for host manipulation. The biology paper notes that the interna is involved in host manipulation, and that these parasites can alter host metabolism, morphology, and behavior. Related genomic work highlights the extensive rootlet system, infiltrating several host organs, and notes specialized structures at the border between parasite and host nervous system that may be sites of host-parasite interaction. So the host is not only physically occupied, it is behaviorally drawn into the parasite's operation as well. A crustacean in this state is still itself, only in a very limited sense. It moves, grooms, broods, and survives, but much of that effort has been redirected. This is where the phrase, already half consumed, becomes almost generous, because some hosts are being used in more than half of the ways that matter. They provide nutrients, they provide movement, they provide reproductive labour, they provide circulation and respiration. The parasite no longer needs to maintain its own ordinary feeding structures because the host has become the feeding system. The parasite no longer needs to court, brood, or defend in the usual way, because the host can be induced to help. What remains of the original animal is still biologically present, but it is no longer operating solely for its own continuation. That is consumption in a deeper sense than merely losing tissue. It is the loss of biological priority. Deep-sea environments do not soften any of this. If anything, they make it easier to understand why such arrangements persist. A body in the abyss is a valuable object. It concentrates nutrients in a place where nutrients are scarce. It moves through darkness using hard-won energy. It crosses large distances. It encounters prey and predators. It is far more useful alive than dead, at least for a while. So parasites that turn hosts into partly consumed, still functional carriers are not bizarre exceptions. They are efficient solutions to a hard problem. The Antarctic copepod work and NOAA's deep-sea pathology material both underline that deep water and bathypelagic fishes do carry such severe mesoparasites and internal larval burdens, and that pathology can include deformation, hemorrhage, organ penetration, and reductions in host condition. There is also a visual cruelty to these cases. Some parasites leave obvious signs: a mouth distorted by an isopod, a copepod trunk trailing from a fish's flank while its anchoring section remains buried in the body, an externa hanging from a crab while rootlets spread inside. These are not hidden infections in the quiet sense. They are living declarations that the host has become a composite object, part fish, part parasite, part crab, part feeding apparatus. The original anatomy is still there but no longer complete on its own terms. And yet many other cases are worse precisely because the signs are subtle. A fish may look merely thin while larval nematodes and cestodes occupy its tissues. A deep-water predator may still swim and feed, while muscle parasites sit near the vertebrae waiting for the next transfer. NOAA's report on deep-sea parasite fauna and the work on deep-water tapeworm larvae show just how common it is for marine hosts to carry larval stages rather than final adult parasites. The body is not always visibly mangled, but it is already being used as a temporary structure in someone else's schedule. From the parasite's perspective, that is enough. From the host's perspective, it means the line between being alive and being consumed has already become uncomfortably thin. This, I think, is one of the hardest ideas to shake once you have spent enough time with marine parasitology. An animal does not need to be dead to be partly lost. It does not need to be torn open to be partly used up. In the deep sea especially, bodies are too valuable to waste all at once. Better to hollow a function, replace an organ, infiltrate a cavity, redirect a behaviour, loosen muscle, deform a liver, feed from the heart, and let the host continue for as long as possible. The result is a population of creatures that are not simply sick or injured, but operating under occupation. And once a host reaches that state, the next question becomes painfully simple. What happens when the host tries to resist? Because bodies do resist. They scar, inflame, clot, encapsulate, groom, and spend precious energy trying to drive invaders back. But in the deep ocean, where energy is rationed and parasites are practiced, resistance is not always enough to reclaim what has already been taken. Bodies do fight back. That is the part worth remembering before we go any farther. A fish is not simply a bag of nutrients drifting through dark water, waiting to be politely emptied by whoever arrives first. A crab is not a passive crate for barnacle larvae with bad intentions. Living things resist. They clot, they inflame, they scar, they wall off intruders, they alter immune signalling, they produce stress hormones, they divert precious energy into damage control. Even in the deep sea, where life is forced to live on narrow margins, hosts are not defenseless in principle. The trouble is that principle and outcome are not always the same thing. A body can do many things correctly and still lose. That really is one of the crueler truths of parasitism. When a predator attacks, success and failure are often immediate. You escape or you do not. With a parasite, the fight can go on for days, weeks, months, sometimes much longer. The host recognizes damage, mounts a response, and tries to contain what has entered. Yet the parasite has been refined by the same evolutionary pressure, and it has arrived prepared for exactly that sort of resistance. In many marine systems, especially in fish and crustaceans, the battle is not one of brute force but of persistence. Can the host isolate the invader quickly enough, cheaply enough, and effectively enough before too much energy is lost? Often the answer is no, not because the host failed to respond, but because the response itself costs so much and the parasite is already where it needs to be. Consider what happens when a parasite enters fish tissue, rather than remaining politely on the outside where everyone can point to the problem. Fish commonly answer internal parasites with inflammation, fibrous encapsulation, and what pathologists describe as granulomatous responses, which is the body's way of trying to wall off something it cannot easily remove. Reviews and histopathology papers on anisakid nematodes describe larvae in fish tissues becoming encapsulated and provoking cellular immune reactions. In plain language, the fish notices the worm, throws immune cells at the area, builds a barrier around it, and tries to convert a moving threat into a contained one. That is a sensible strategy. It is also expensive, and it does not necessarily eliminate the parasite. The larva may remain alive inside that capsule, waiting patiently for the fish to be eaten by the next host. The fish fought. The fish responded. The fish still became storage. There is something especially bleak about encapsulation when you think about it for more than a moment. It sounds like victory at first. The host sealed the intruder away. The problem was contained. But if the parasite remains viable inside the capsule, then the host has not really won. It has merely reorganized the terms of occupation. The enemy is still present. Tissue has been lost to scarring. Energy has been spent. Inflammation has altered normal function. The host may go on swimming through the dark with a collection of little internal prisons, each one built at its own expense, each one still sheltering the thing it was meant to defeat. It is less a triumph than a stalemate in which only one side actually needs the body to stay functional. The same sort of grim bargain appears with acanthocephalans, the thorny-headed worms that attach with hooked proboscises to the gut wall. A 2024 review notes that these parasites can penetrate deeply into the fish intestinal wall and trigger severe pathological reactions. It also notes that heavy acanthocephalan burdens can affect the fish's nutritive status, including reduced liver weight in cod under high parasite loads. So the host does respond. There is tissue reaction. There is damage, there is physiological cost, yet the worm remains anchored, absorbing nutrients and continuing its life. The gut, which should be the place where the host finally gets something back from its hard-won meals, becomes another site where effort is redirected outward. The fish eats, the parasite collects, the body protests, the body still loses ground. What makes this worse in the deep ocean is that the host usually cannot afford much waste. A surface fish in a productive system may have a slightly better chance to recover from blood loss, tissue damage, or reduced feeding efficiency simply because meals are more available and the environment is less energetically severe. A deep-sea fish does not live with that comfort. If it spends energy on immune activation, tissue repair, stress responses and altered behaviour, that energy comes from reserves it may already be struggling to maintain. The defence itself can become part of the harm. In the abyss, fighting back is not free. It is another bill added to a host already carrying the parasite's invoice. This becomes particularly clear with blood-feeding micro-predators such as gnathiid isopods. Experimental work on fish infected by a single gnathiid found that infection significantly reduced fast start escape performance and routine swimming behaviour, while cortisol levels nearly doubled. In other words, the fish did exactly what a vertebrate under attack is supposed to do. It entered a stress response. Hormones shifted. Physiology changed. The body registered the problem immediately. But those very changes were accompanied by poorer escape performance and reduced activity, both of which matter enormously when you're a small fish in a world full of things trying to eat you. The host's reaction was real. It still left the host worse at surviving the next danger. That study was done in reef fish rather than in deep-sea species, but the principle carries very neatly into deeper water. A fish weakened by blood loss and stress does not need to die on the spot for the parasite to succeed. It only needs to become slower, more tired, less responsive, or slightly worse at the next crucial movement. In the deep sea, where prey encounters are fewer and missed opportunities more costly, a small decline in locomotion or escape can matter a great deal. A host that fights back hormonally and immunologically may still emerge less capable than it was before, which is often enough for the parasite's interests. Sometimes the host's resistance is visible in wounds and local damage. Sometimes it is visible only in chemistry. A 2023 study on fish infected with the cymathoid isopod, Cymathoa eremita, found significant reductions in respiratory burst activity and myeloperoxidase activity, both important parts of innate immune function, even while immune-related genes were upregulated in certain tissues. That is a wonderfully depressing biological picture. The host clearly recognizes the parasite and activates parts of its immune machinery, but some functional immune measures are still reduced. It is as if the body is shouting the alarm while finding that some of the fire hoses have lost pressure. The response exists, the system is still compromised, and that sort of mixed result is common in host-parasite interactions. A parasite does not necessarily need to shut down every aspect of immunity. It only needs to endure the parts that cannot remove it and exploit the resulting chaos. Infected tissue may show inflammation and gene activation, while the host as a whole becomes drained, stressed, and less effective at other defences. The immune system is not a single switch. It is a costly orchestra, and parasites are very good at continuing their meal, while the host spends energy trying to keep the musicians playing. By the time that effort is underway, the parasite is often already anchored, embedded, or hidden in a body compartment where complete removal is unlikely. Crustaceans present a different version of the same tragedy. They do not have vertebrate immune systems, but they do have innate defences, circulating blood cells called hemocytes, clotting mechanisms, encapsulation responses, and a variety of biochemical tools for dealing with invaders. Rhizocephalan barnacles, however, are specialists in getting past those defences. A 2021 proteomic study on the Chinese mitten crab, infected with Polyascus gregaria, found hundreds of differentially expressed proteins, and identified immune-related pathways involving lysosomes and autophagy. The crab was responding. It was not inert. At the protein level, infection had clearly shifted the host's physiology. Yet the parasite still established itself, still developed its internal root system, and still continued using the crab as host. The resistance was measurable. The occupation continued anyway. There is also evidence that hosts can sometimes encapsulate rhizocephalan rootlets, which sounds briefly encouraging until you realise that the parasite's entire history is one of refining ways around precisely that problem. Reviews of rhizocephalan manipulation note that host immune responses such as encapsulation can occur, but successful rhizocephalans still infiltrate tissues, alter host biology, and maintain the internal root network that feeds them. The crab once again is not failing to notice. It is losing a contest against something extraordinarily adapted to being noticed, and surviving anyway. The parasite has not won because the host is foolish. It has won because the host is expensive to defend, and because the parasite arrives with a design built to exploit exactly that cost. There is something grimly practical about how these parasites turn the host's own priorities against it. Healing a wound takes resources, encapsulating a larva takes resources, producing immune proteins, replacing damaged cells, and maintaining inflamed tissue all take resources. In the deep sea, resources are not waiting in abundance. A fish or crustacean that spends energy on defense may have less for growth, reproduction, movement, or simple maintenance. So even when the host responds effectively at a local level, the wider cost can still be severe. The parasite may not need to break the immune system outright. It may only need to force the host into an expensive war of attrition that the host cannot sustain without losing elsewhere. That is why fights back and still loses is not just a dramatic phrase. It is often the literal pattern. The fish walls off the anisakid larva, but the larva remains infective and the fish carries scarred tissue. The gut reacts to the thorny-headed worm, but the worm remains attached and the host's nutritive state declines. The crab shifts its immune proteins and innate pathways, yet the rhizocephalan still extends its rootlets and redirects the host's body. The fish stressed by a gnathiid shows elevated cortisol, but it also becomes slower and more vulnerable. Resistance happens. It simply does not always restore the body to itself. Some of the saddest cases are the ones where the host's behaviour remains broadly normal. A fish keeps feeding, a crab keeps grooming, an infected animal continues the ordinary motions of life while its tissues are inflamed, its reserves are reduced, and its defences are already busy. From a distance, this can look like tolerance or adaptation. Sometimes it is, but sometimes it is simply the only option available. A host does not get to step out of the ocean and rest for a week while its immune system sorts itself out. It has to keep moving, keep feeding, keep avoiding predators, all while paying for the ongoing conflict inside or on its body. The parasite relies on that. A living host with no time to recover is far more useful than a dead one drifting uselessly into the dark. There is also the matter of secondary effects. Wounds made by blood feeders can become entry points for microbes. Tissue penetrated by copepods or worms may become deformed or weakened. Chronic inflammation can alter nearby organs. Blood loss can reduce performance. Even where the parasite itself does not deliver the final blow, it opens doors and creates conditions in which other problems become more dangerous. The host may not die of the parasite in the neat diagnostic sense people like. It may die because the parasite made everything else harder. Harder to breathe, harder to feed, harder to escape, harder to heal, harder to survive one more day in a place already run on strict budgets. And I think that is what makes these host parasite struggles so haunting, compared with the clean violence of a predator strike. A predator at least announces the conflict. With parasites, the struggle can remain hidden, prolonged, and strangely quiet. The body responds in all the ways it knows how. Cells gather, fibers thicken, genes switch on, stress hormones rise, local tissues try to wall off what has entered. Yet the invader often remains, feeding or waiting or reproducing while the host absorbs the cost of trying not to lose. It is the sort of fight where effort does not guarantee recovery, and courage, if one can use that word for physiology, is no protection against being out-adapted. The deep sea favours exactly these grim compromises because it does not reward waste, and it does not hand out surplus. Parasites there do not need theatrical dominance. They need to endure host defences long enough for those defences to become one more burden the host must carry. A body inflamed, stressed, scarred, and still swimming is, from the parasite's point of view, a functioning arrangement. The host has fought back. The host is still losing, and once you begin to see how often that happens, the larger shape of the deep ocean comes into view. It is not simply a place where strange parasites exist. It is a place whose darkness, scarcity, and distance have helped produce exactly these ruthless, efficient relationships in the first place. The deep sea favours exactly these grim compromises because it offers almost none of the comforts that make gentler strategies easy. Noé defines the deep ocean as the part of the sea typically deeper than 200 metres, where conditions are dark, cold, food poor, and subject to intense pressure. Noah also notes that there is rarely significant light beyond 200 metres, which means the great majority of the deep sea operates without sunlight as a dependable daily energy source. That single fact shapes nearly everything else. A world without light is a world without ordinary photosynthesis, and a world without ordinary photosynthesis is a world where food usually arrives late, damaged, or already half used by something else. Pressure adds another cost immediately. NLOA states that hydrostatic pressure increases by roughly 1 atmosphere for every 10.06 metres of depth. At a few thousand metres, that becomes an enormous physical burden on bodies, cells, membranes, and movement. Cold comes with it. NOAAs. Ocean Service explains that deep water is cold because dense, salty, cold water sinks and fills the deep basins, and NOAA's ocean layer material notes that bathypelagic temperatures stay near 4 degrees Celsius. So animals in the deep are not only hungry in a dark place, they are hungry in a cold place under crushing pressure. Nothing about that combination encourages waste. That is the first reason the deep ocean breeds ruthless life. Ruthless does not necessarily mean aggressive. It means efficient. It means any body plan or behaviour that saves energy, secures food, or reduces uncertainty is more likely to last. In a bright, productive surface environment, there may be room for speed, display, experimentation, and the occasional bad decision. In deep water, bad decisions are expensive. Chasing prey over long distances is expensive. Missing a hunting strike is expensive. Maintaining large active tissues is expensive. A parasite that can skip those costs by anchoring to a host or living inside one is not breaking the rules of the deep sea. It is following them very closely. That is an inference from the physical conditions NOAA and MBARI describe, but it is a strong one. Food scarcity is probably the clearest pressure of all. NOAA and MBARI both describe marine snow, the constant fall of dead plankton, fecal pellets, mucus, and other debris from surface waters as an important or primary food source for many deep-sea animals. NOAA's own explanation says many animals in the dark parts of the ocean filter marine snow from the water or scavenge it from the seabed as their primary food source. MBARI says much the same, noting that sinking particles are an important source of food for deep-sea animals, protists, and bacteria. That is a remarkable basis for an ecosystem if you stop to think about it. It means vast communities are sustained not by a local garden of constant growth, but by whatever scraps happen to drift down from far above, and scraps create a certain kind of life. If your food arrives as irregular drifts of debris, then success depends on patience, specialization, and the ability to exploit concentrated opportunities whenever they appear. MBARI describes abyssal life as usually not getting much to eat, with marine snow as the main food source for animal and microbe communities. NOAA similarly says food is scarce in the dark depths, and that drifting material from above is therefore an important part of the food web. Under those conditions, a host body becomes an unusually valuable object. It is not just meat, it is concentrated nitrogen, carbon, fat, minerals, blood, shelter, motion, and in many cases a way to reach the next predator in the chain. For a parasite, that makes a living host better than a random food particle by several orders of magnitude. This is why the deep sea tends to reward any strategy that turns uncertainty into access. A predator may spend time and energy searching for prey and still miss. A scavenger may wait for a carcass that never comes. A parasite that successfully enters a fish, crustacean, squid or shark has converted an unpredictable world into a more regular one. The host does the searching, the feeding and the moving. The parasite taps into the result. That is not kindness, and it is not dramatic villainy either. It is the sort of plain efficiency that extreme environments repeatedly produce. When the background conditions are hard enough, life starts selecting for methods that look merciless simply because gentler methods keep failing. Cold reinforces this pattern in a second way. MBARI notes that the frigid temperatures of the deep sea slow metabolism and developmental rate in deep sea octopuses, and its work on a newly described deep sea slug found a much lower metabolism than in shallow water relatives, reflecting what it called the slower pace of life in the deep water column. Cold does not just make everything slower in a pleasant, restful sense. It slows growth, reproduction, movement, and in many cases recovery. So when a parasite drains blood, damages gills, occupies muscle, or provokes chronic immune responses, the host may have fewer physiological opportunities to compensate quickly. A small burden can last a long time because the whole system already runs slowly. That slower pace has another consequence. If development is delayed, then the value of staying alive long enough to mature becomes even higher. Many deep-sea species are already working on long schedules. They cannot afford to throw resources away casually, and parasites benefit from that. A host adapted to conserve energy and continue functioning under difficult conditions is exactly the kind of host a parasite wants. The fish or octopus may be built to endure scarcity and cold, but those same traits can also make it a durable platform for blood feeding, internal encystment, or long-term tissue occupation. In other words, deep-sea resilience can be turned into parasitic opportunity. That is an inference, but it follows directly from the established facts about slow metabolism, scarce food, and long life processes in deep water. The deep sea also operates on feast and famine events rather than steady abundance. NOAA says whale falls provide a sudden concentrated food source, a bonanza for deep sea organisms, and National Marine Sanctuaries notes that whale falls can feed communities for years to decades. MBARI goes even further, reporting that one whale fall can deliver as much organic material as several thousand years' worth of marine snow. That is not a small adjustment to a food budget. That is a complete interruption of the usual rules. In a place where most food arrives as thin drift, a whale carcass is a violent excess. Life in the deep sea is therefore shaped not only by chronic scarcity, but by rare episodes of abundance that reward anything able to detect, reach, exploit, or remain attached to concentrated food sources quickly. That feast and famine structure helps explain the deep ocean's hard edge. When food is usually scarce but occasionally overwhelming, organisms are selected both for endurance during lean times and for ruthless efficiency during rich times. Scavengers converge fast. Competitors crowd in. Parasites that can spread during those gatherings benefit. Hosts weakened by crowding, wounds, or poor condition become easier to exploit. The same logic appears around hydrothermal vents and cold seeps, though there the abundance comes from chemistry rather than falling flesh. NOAA's chemosynthesis and hydrothermal vent fact sheets explain that chemosynthetic microbes form the base of food webs at vents and seeps, and that vent sites can become oases of life where food is plentiful and easy to obtain, with animals often present in very high abundance. Even in the deep sea then, abundance exists in patches, and patches create dense biological traffic. Dense traffic is very good news for parasites. There is an important contrast hiding in that point. The average deep sea is food poor, but some deep sea places are food rich because of whale falls, vents, seeps, or sudden pulses of sinking organic matter. Ruthless life thrives in both settings, but for slightly different reasons. In the broad food-poor background, parasitism is useful because it secures a stable resource. In localized food-rich oases, parasitism is useful because many bodies gather together and transmission opportunities increase. The first rewards patience. The second rewards timing. Put the two together across millions of years, and you get an ecosystem in which parasitic strategies are not rare accidents but recurring successes. Darkness matters too, and not just because it makes the place feel more cinematic. In darkness, detection changes. Visual signalling weakens. Hunting and avoiding being hunted rely more heavily on scent, touch, vibration, and opportunism. That can favour predators with ambush tactics, scavengers that home in on chemical trails, and parasites whose larval stages drift until contact is made. NOAA's deep ocean habitat facts emphasise that the physical environment is radically different from surface habitats because of limited light, pressure, and cold. In such an environment, a parasite that does not need to identify prey visually or chase it actively has an advantage over one that does. It can rely on currents, ingestion, contact, or host habits instead. That is one more reason ruthless but low-motion feeding strategies do so well in the dark. Scarcity also narrows the margin for defensive luxury. MBARI describes many deep ocean animals as already living on the edge because of cold, low oxygen conditions and limited food availability. If that is your starting point as a host, then immune responses, wound repair and tissue replacement are expensive undertakings. A parasite does not need to overwhelm every defense completely. It may only need to impose enough chronic damage that the host's repair costs begin to matter. That is how apparently modest parasites become ecologically serious. They exploit systems already running close to their limits. In the deep sea, the cost of fighting back is part of the parasite's weaponry, even if the parasite never consciously intended it that way. There is another structural reason the deep ocean breeds harsh solutions. Much of deep sea life is connected by long food chains that move carbon and nutrients downward and upward through predation, scavenging and repeated recycling. NOAA's marine snow materials, whalefall fact page, and vent fact sheets all underline that deep sea communities are built around transferred energy rather than local sunlight-based production across most habitats. In systems like that, trophic transmission becomes a very effective parasitic strategy. If one animal reliably eats another, a parasite can use that act as transportation. The deep sea does not invent this logic, of course, but it rewards it strongly because direct opportunities are patchy, and prey are often swallowed whole or in large pieces. That final point is an inference from the ecology of marine predators and parasite life cycles, but it fits the documented prevalence of multi-host marine parasites. The result is a world where being alive often means being useful to something else in more than one way. Your blood is food, your tissues are housing, your muscle is transport, your gut is an anchor site, your behaviour may become a delivery mechanism, your reproductive system may be redirected. In a richer, brighter environment, there might be enough alternate routes to make such extreme dependence less widespread. In the deep sea, a living body is one of the few concentrated, organised packages of energy available. It would be surprising if evolution did not repeatedly find ways to exploit that fact. In that sense, the deep ocean does not merely tolerate ruthless life. It encourages it by making bodies more valuable than almost any drifting scrap around them. Even the apparent exceptions, the lush communities at vents and seeps, do not really soften the picture. NOAA's materials describe these sites as oases of life with abundant food, but also as volatile, localized systems dominated by relatively few types of organisms. Abundance there is intense, but it is not evenly distributed, and the habitats themselves can be short-lived or patchy. That kind of environment still favours specialisation, rapid exploitation, and close dependence on whatever stable resource is available. Ruthlessness does not disappear when food becomes chemically abundant in a vent field. It simply changes costume. The same basic rule remains: waste nothing, miss nothing. Turn every available body, current and chemical gradient to your advantage. There is also a reason this ruthless quality strikes us more strongly in the deep sea than in many land environments. On land, we are used to visible competition, teeth, claws, pursuit. In the deep sea, the same struggle is often hidden inside slow systems. A host may look almost calm while carrying internal larvae, embedded copepods, blood-feeding isopods, or a root system from a parasitic barnacle. The environment itself supports that hiddenness. Darkness conceals, distance conceals, slow metabolism conceals, rare observation conceals. By the time we notice the relationship, it often looks less like a fight and more like a completed arrangement. That does not mean the deep sea is uniquely cruel in some mystical way. It means its physical conditions reward quiet, efficient, deeply integrated forms of exploitation that are easy to miss and difficult to reverse. So when we ask why the deep ocean breeds such ruthless life, the answer is not that something about darkness makes organisms evil, which would be a dramatic but unhelpful reading. The answer is more ordinary, and, for that reason, more convincing. The deep ocean is cold, dark, pressurized, and often short on food. Energy usually arrives from above as marine snow, sometimes as carcasses, and in special places through chemosynthesis. Many animals live slowly, close to physiological limits, and many resources are concentrated in the bodies of other organisms. Under those conditions, life repeatedly favours strategies that reduce uncertainty and extract value with precision. Parasitism is one of the best such strategies ever invented. That is why the parasites we have been following tonight are not odd accidents or decorative horrors added for effect. They are products of the deep sea's basic economy. Hooks, rootlets, blood-feeding mouthparts, tissue cysts, host manipulation, all of it makes sense once you accept the terms of the place. If food is scarce, secure a host. If movement is costly, borrow a body. If abundance comes rarely, hold on when it does. If the host fights back, outlast the cost of that defence. The abyss does not ask life to be noble, it asks life to persist. Over enough time, persistence starts to look very much like ruthlessness. And once you see the deep ocean that way, the final step is not really another descent into anatomy or pathology, it is a quieter thought than that. All the blood taken, all the organs occupied, all the bodies borrowed, all the small hidden battles in black water, they are still happening now whether anyone looks down or not. Which leaves us with one last part of the journey, and one final look at what it means that beneath the calm surface of the sea, the feeding has never really stopped. And so, after all of that, the strangest parts may be this. Nothing we have talked about tonight belongs to some vanished age of the ocean. These are not old experiments that nature tried once and abandoned. The darkness below is still active. The deep ocean still begins beyond roughly 200 metres, where sunlight drops away and conditions turn cold, pressurised and food limited, and the animals living there are still surviving under those exact terms. That matters, because it means the logic we have followed from one parasite to the next is not theoretical. It is ongoing. Marine snow still drifts downward through the water column as one of the basic food inputs for deep-sea communities. Whale falls still deliver sudden, concentrated bursts of organic matter to the seafloor. Hydrothermal vents and cold seeps still create pockets of abundance in otherwise difficult environments. And in all of those places, one basic rule keeps holding steady. A living body is one of the most useful concentrations of energy the deep sea can offer. Once that rule is in place, much of the rest follows with uncomfortable clarity. A parasite that can attach to a fish, burrow into tissue, drink blood, occupy a mouth, spread rootlets through a crustacean, or wait quietly in muscle until the host is eaten has not stepped outside the ecology of the deep. It has fitted itself to it. That is why marine parasitism is so persistent and so varied across fishes, crustaceans, sharks, rays, and other ocean animals. The strategy keeps paying off. There is also something worth saying plainly here. Parasites are easy to treat as villains because they trigger a very old kind of disgust in us. Teeth are one thing, hooks are another. But something small living inside something larger, feeding slowly, changing behaviour or replacing tissue, tends to bother people in a much more intimate way. It feels invasive because it is invasive. It feels unfair because the host often keeps going while losing piece after piece of itself. Yet from a biological point of view, parasites are not aberrations. They are major participants in ecosystems, and marine scientists have long emphasized that parasites can shape host populations, food webs, and the movement of energy through the sea. That is one reason the deep ocean becomes even more interesting and more unsettling the longer you think about it. Most of the sea is not a bright, open expanse of simple predator and prey drama. Most of it is hidden from ordinary view, and much of what happens there is slow. A fish can carry larval worms in its tissues for long periods. A copepod can remain anchored while the host continues swimming. A crustacean can be infiltrated internally by a parasitic barnacle, whose feeding structures spread through the body while an external reproductive sac hangs outside. These are not quick stories. They are long arrangements, and perhaps that is why the deep sea leaves such a strong impression once you start learning about it. The violence there is often quiet, not absent. Quiet. A shark taking a fish is obvious, a fish carrying a tongue-replacing isopod, a blood-feeding parasite in its gills, and larval stages in its musculature is something else. The body remains in motion, the life continues, but it continues under occupation. Smithsonian's overview of ocean parasites and NOAA's fish pathology work both make clear that marine hosts can remain alive and functional while carrying parasites that alter blood supply, organs, feeding structures, or general condition. If there's any comfort in this, it may be that the deep ocean is not malicious, it is demanding. That is different, even if it does not always feel kinder. The physical realities are straightforward enough. Light disappears, pressure rises, temperatures stay low, food is limited across enormous areas. Under those conditions, evolution repeatedly favours strategies that conserve energy and improve certainty. That is why some creatures ambush, that is why others scavenge, and that is why parasitism does so well. A host solves too many problems at once to be ignored for long. Seen that way, the deadliest deep-sea parasites are not random horrors, tucked away in the ocean like a collection of unfortunate secrets. They are the practical result of life working with the materials available. Blood is useful, tissue is useful, a moving body is useful, a host that can be eaten by a larger predator is especially useful. Even behaviour becomes useful if it can be bent just enough to improve transmission. Marine parasitology studies repeatedly describe exactly those functions: tissue occupation, blood feeding, trophic transfer, host manipulation, and long periods of persistence inside or on the host. It is also worth remembering how incomplete our view still is. NOAA and other ocean research groups repeatedly stress that the deep sea remains difficult to access and far less explored than many surface environments. New species continue to be described. New observations continue to refine what we think we know about deep water ecology. So even after everything we have covered, There is no good reason to imagine we have already found every strange parasitic arrangement the ocean has produced. If anything, history suggests the opposite. The more closely we look, the more the sea reveals systems that would have sounded exaggerated before they were documented. That thought has a peculiar effect on the imagination. It does not necessarily make the ocean feel hostile, it makes it feel busy in ways the surface never shows. A calm sea at night can look almost empty. A flat horizon can suggest stillness. But below that surface, below the reflected moonlight or the daylight glitter or the grey weather of an ordinary afternoon, bodies are still moving through black water under pressure. Fish are still carrying hidden burdens. Parasites are still feeding, waiting, reproducing and transferring from one host to the next. Marine snow is still falling. Scavengers are still converging where something large has died. The system is not paused just because we are not looking. There is, in a strange way, a lesson in that. We tend to imagine nature as most real when it is most visible to us. The breaching whale, the leaping tuna, the coral reef in full colour. The deep sea resists that habit. It reminds us that some of the most important biological relationships on Earth are happening in darkness, at low temperatures, under immense pressure, in forms that do not seek our approval and are not simplified for our understanding. Parasites belong to that hidden majority. They do not advertise themselves as heroes or monsters. They simply continue doing what works, and what works down there is often patience. A parasite does not have to outrun a host if it can enter it early and wait. It does not need a spectacular attack if it can drink blood in small, steady meals. It does not need to chase in open water if a food web will deliver it upward through predation. It does not need to build a conventional body if the host body can be turned into feeding equipment. Those are efficient solutions in a difficult environment. Disturbing solutions, certainly, but still solutions. The published marine literature on anasacids, acanthocephalans, parasitic copepods, cymathoid isopods and rhizocephalans keeps returning to those same themes of persistence, transfer, tissue occupation, and host use. At the same time, it would be too simple to say the host is always helpless. Hosts do resist. Fish encapsulate larvae. Blood parameters shift. Immune tissues respond. Crustaceans alter hemocyte and protein activity. Wounds clot and inflame. But as the studies we drew on show, those responses often come with serious costs, and they do not always remove the parasite. In some cases, the response contains the invader without eliminating it. In others, the stress of the defense itself leaves the host weaker. The body fights, the body survives for a while, the parasite remains. That may be the most honest way to understand deep-sea parasitism, not as a parade of unbeatable monsters and not as a collection of harmless curiosities, but as repeated examples of life finding ways to live off life under hard conditions. Some arrangements are brief, some are catastrophic, some are so integrated that the host and parasite begin to look, for a time, like a single troubled machine. The deep sea contains all of those forms because it allows very little waste and very little sentiment. And yet, for all their ugliness from our point of view, parasites also reveal something precise about evolution. They show just how far adaptation can go when survival depends on solving one narrow problem well. Hold on. Get inside. Stay alive. Reach the next host. Avoid being removed. Reproduce before the opportunity ends. That is the whole script, and over millions of years it has produced tongue-replacing isopods, hook-headed worms, tissue-boring copepods, blood-feeding sea ticks, and barnacles that no longer bother with an ordinary digestive tract, because they have converted another animal into one. Those are astonishing outcomes, even if astonishing is doing a great deal of work in that sentence. By this point in the journey, the ocean may feel a little different than it did at the beginning, perhaps broader, but also more crowded, less empty, less innocent. The sea has always had a way of hiding complexity under smooth surfaces, and the deep portions hide it especially well. Looking out across water, it is easy to think in terms of distance and calm. It is harder to think about the fish below carrying wounds in the gills, larvae in the flesh, or a parasite where a tongue should be. Harder still to picture a crab tending the brood sac of a parasite that has spread rootlets through its body. But those images are part of the real ocean too. That does not make the sea lesser. If anything, it makes it more honest. Real ecosystems are not built from beauty alone. They are built from use, scarcity, conflict, recycling, persistence, and compromise. The deep ocean simply makes those terms harder to ignore. It strips away the colourful distractions of shallow water and leaves behind a very direct economy. Eat what you can, hold what you can, outlast what you can. The parasites we followed tonight are, in their own terrible way, among the cleanest expressions of that logic. So now, at the end of this quiet descent, what remains is not only the image of monstrous little feeders lurking below, though they do remain busy as ever. What remains is the understanding that the darkness is full of systems still working, still feeding, still trading energy from one body to another, still writing those hidden relationships into flesh and blood and bone and shell. The ocean surface may close over all of it without a mark, but underneath, the process does not stop. It has not stopped for millions of years. And if this slow trip through the deep helped settle your thoughts a little, or gave your mind something strange and steady to follow for a while, I would be very grateful if you gave the video a like and maybe subscribed as well. It helps this small, quiet corner reach other people who enjoy ending the day with science, mystery, and the occasional completely unreasonable parasite. For now, let the ocean return to darkness. Let the hosts keep swimming, let the feeders keep feeding far below the reach of light, and let the surface for just a little while look calm again.